So the first session is on opportunities and risks for foundation models. So we'll start with our first keynote talk by Jack Clark. Jack is the co-founder of Anthropic, an AI safety and research company working on building reliable, interpretable, and steerable AI systems. He's also co-chair of AI Index, which tracks AI trends over time. And previously was a policy director at OpenAI, where he helped shape policy around efforts like GPT-3. So Jack, the floor is yours.
Thank you very much, Percy. And I promise that Percy and I didn't coordinate, but I am going to give a presentation that makes a couple of points that Percy made, albeit in perhaps a slightly blunter form. So what I'm going to talk about today is how, and I'm going to get to why I'm using the term big models, but big models, foundation models are becoming part of the ecology of the internet. They're going to change sort of the environment that we all operate in. And at the same time, they're going to be influencing the power relationships between different AI actors. This presents opportunities for coordination. It also presents some risks which we need to pay attention to. And I think that these models represent a real grand challenge for society to try and analyze and sort of integrate safely. And as Percy's alluded to, these can be incredibly useful tools, and they could also be harmful via bugs or harmful via the fact that they're capable. So I'm going to give a sort of an overview talk which tries to touch on some of these issues, and where Percy's covered a couple of the same things, I'm going to go relatively quickly. So first, what are these models? Well, the foundation models paper from Stanford just sort of defines them as models trained on broad data at scale that can be adapted to a broad range of downstream tasks. Examples are BERT, GPT-3, and CLIP. I think that's pretty good. I prefer a slightly different definition, which is I think of these models as big models. And the reason why I think of them as big is that I think that one of the effects of these models is their resource intensity. They cost a lot to train, they cost a lot of data to be sort of dumped into them, they require a lot of engineering resources, and it's that bigness, that scale, which relates to sort of the power that these models have and how they change power relationships in AI development. So that's why I'm using this term, but I think foundation models captures them technically quite well. So let's just quickly refresh on why we care about these models, because as Percy said, these models can do few-shot learning, so they can generally be adapted to a very, very broad range of downstream tasks. And they also natively have just a huge range of capabilities. We have models that can do, in the same model, text generation, text classification, string prediction, the same techniques you use to train foundation models for text, you might use to train models to do material science or chemistry analysis, and it's all going to lead to a sort of similar property. They can do data transformation, and as people likely know, data transformation is just an incredibly economically valuable thing. So it partly explains why these are being deployed so broadly. And these models can be plugins to other models. They can become the world models for other systems like robots or other things which other panelists are going to talk about. So on the flip side of these capabilities are these issues. Percy did a good job of going over those, so I'm going to go quickly here. But as we know, they have biases. They have the potential to give inappropriate responses. They have the potential to give dangerous responses, as in you could ask a model how to build a bomb, and eventually it might tell you how to build a bomb, which is something that raises a broad set of confounding issues. They have this broad potential for utility and also this broad potential for sort of misuse. And probably most importantly, they're kind of difficult to interpret currently. We know that these models can do a broad range of things, but we don't necessarily know what is going on inside the model that lets them do these things. And it also relates to our ability to characterize capability emergence. We know that things emerge out of these models as you train them, new capabilities, many of which are desirable, but we don't really understand the process by which that emergence occurs, and we can't really predict what capabilities are going to come out of a big training run. So this presents huge opportunities and challenges. And a good conceptual frame I've found for thinking about these models is I think of them as funhouse mirrors. And what I mean by that is any sufficiently large model will take in a huge amount of data and it will magnify some of that sort of data and minimize other bits. And what this means in the context of these models is certain types of culture get magnified by these models, certain types of culture get minimized, certain identity groups get maximized, certain identity groups get minimized, stereotypes get maximized, stereotypes get minimized, you get the picture. And this is a huge issue. It means that these models have different behaviors for different parts of the sort of landscape they've been trained on. And where these models intersect with culture is where a huge range of really complicated issues start occurring to do with bias, to do with how these models behave for different groups of people, to do with effectiveness. And I think that using this frame of sort of a funhouse mirror gets at some of the challenge here, where we know these things are useful, but they have this very challenging property. And as Percy said, but we really do need to emphasize this, these models are being deployed right now. It's very much not like an academic concern anymore, it's an economic concern. And when things shift into economic concerns, power dynamics change. And you start to enter a world where huge amounts of capital have interest in the deployment and development of these models. And when capital has interest in something, it tends to want to benefit the most capital-oriented entities, which doesn't necessarily include academia or civil society or government. So we're in an incentive structure currently that points us towards these models being developed primarily by sort of capital-oriented actors and not by the whole of society. And as I'm going to get to later in this talk, I think that that's one of the really big issues we need to grapple with at this conference today. So who's building them? You know, the GPT-3 replications that exist are by OpenAI, the originator, Huawei, a Chinese telecommunications company with a good research team, and AI21 Labs, which is an Israeli startup. There are also replications being worked on by Sberbank, which is a really, really big bank in Russia with a good AI research team, and by some other entities, many of which are companies, and all of these public replications are companies. There have also recently been code models developed, and these code models, much like foundation models, are trained on very, very large amounts of code, have capability emergence, have broad utility, have some challenges, but all of the people developing them are companies so far, specifically Microsoft, GitHub, and OpenAI via Copilot, OpenAI via its own service Codex, and Google just published a paper on program synthesis with large language models that indicates it's thinking intently about this area as well. This fits into a broader pattern that we really need to emphasize, which is that if you look at recent breakthroughs in AI research, and by a breakthrough, I mean something that was notable to people in the field and or economically useful and was subsequently integrated into business, you notice that there's a correlation between these things and compute usage. And specifically, you're seeing the amount of compute being used to train these things go up over time. At the same time, we're seeing the actors developing these models change from academia to companies. Here's a graph from OpenAI, which I and my colleagues did on analyzing these large compute items. And all I've done is I've marked up which bits were developed by companies and which bits were developed by academia. And it's quite striking. The majority of these things in recent years were developed by corporate actors and not academia. And if you go back in time, it didn't used to be this way. If we go and look at the earlier era of AI development, important things were developed predominantly by academia. Academia built early self-driving car prototypes. It built early speech analysis systems. It built a lot of the early primitives for deep learning by Geoff Hinton and others. And you see some corporate activity, like IBM built a good system that could play backgammon. Yann LeCun at Bell Labs built LeNet. But it's actually a more even world. So we have to focus on this because the actors that get to develop this stuff determine the future of it in a large part. And currently, the actors developing this stuff are predominantly companies. So why is that? Well, speaking a little bit from experience at OpenAI and at my current place, Anthropic, for some fairly obvious reasons. These models are expensive. It costs hundreds of thousands to millions of dollars to train them, so you need some money allocated. They're also models that take time. These models take weeks to months to train. That means that you need to babysit them during training. You need to wake up in the middle of the night and notice that your loss curve has exploded and roll your model back to an earlier snapshot and do all kinds of maintenance of it, which is not particularly glamorous and is also sort of an artisanal science right now, but isn't that well documented. In addition, these models have less inherent attraction to certain incentive structures in academia because they're, as Percy said, they are simple. They're based on a decade-old technique. We've just scaled up a lot of data and compute, so they don't have some of this inherent novelty that academia rewards. And there's just a lot of engineering work rather than pure theory work. Industry rewards this in the form of money and career advancement. And academia, at least in ML, doesn't so much, although I think that some of that is changing. So this leads us to the complicated issue that we need to work on at this workshop, which is that the people that get to use these models are the private sector actors who build them, and the people that the private sector actors sell their models to, so developers via an API, and academia, but only via access programs. And I'm not picking on Facebook here. I just think Facebook generates a lot of these examples, but Facebook is an example of a large tech company that periodically does access programs for academia to look at certain bits of its data. Then academia finds out something that doesn't play favorably for Facebook, and Facebook revokes the access. It would be naive to think this won't happen in the AI community. And I'm not saying that to suggest that companies doing academic access don't have good intentions. They all have good intentions. They're all run by people who are reasonably nice, we're all human, but they all have incentives, and these incentives are generated by capital, and these incentives will at some point mean that access will be taken away. And so if access is taken away and academia isn't building these models, a really bad set of things happen to do with a lack of accountability, unconstrained deployment, and a very uneven world. Additionally, access programs, make academia in some sense dependent on the private sector. And that's a bad thing because, as Percy said, these models have issues. They have really complicated issues which need to be worked through. And these issues are not going to be that fun to work through. They are going to be they're going to deal with some of the issues that we as societies have completely failed at solving so far, like bias. So to expect that conversation to sort of have the best chances of going well, you want all of the people in that conversation to have leverage. And currently, all of the leverage is held by a small set of private sector actors, which means that they are not incentivized to have an equal conversation. They're incentivized to exploit that power differential. And again, we should assume that this will happen based on the incentive structure. So why should academia build this, even though it's very expensive and challenging? Well, I think as I've mentioned, it's all about leverage. Information is power. We want more information about these models to be broadly available, and we want it to be broadly distributed. And if we don't do this, then students go to industry to learn how to build these models. Many of them probably stay in industry and don't cycle back into academia. Academia gets trapped into dependency on the private sector for model access, which is not going to lead to anywhere particularly great in the long term. The private sector gets to shape the regulatory environment because it will have the models and it will generate information about the models and it will do its own studies and it will partner with friendly institutions and it will use all of this to shape the policy environment in which these models are deployed, and academia won't have as much leverage. And academia won't be able to it'll be able to critique, but not necessarily propose alternatives. It's easier to get an alternative to become true if you can prototype it. And prototyping stuff here requires developing or analyzing and developing models of this kind of class in terms of scale and magnitude of resources. So final couple of points, and then we'll go to Q&A. What will these models do in the world? Well, as I said, the internet is an ecology of systems. The interactions of these entities in this ecology lead to societal changes. Good examples are just to look at the internet for the last 10 years or so, where the emergence of platforms like Facebook and Twitter and aggregators like Google has centralized human eyeballs onto a small number of platforms, mirroring the economy of scale effects we see everywhere else in the economy. At the same time, these platforms are starting to recommend stuff to users via increasingly complicated and inscrutable AI models. And actually, we know that it's changing stuff. My media habits have changed because of YouTube's recommendation algorithm. I bet yours have as well. And this has effects ranging from the benign, in that I now know a lot about like how cheese gets made, because I like watching cheese making videos for some reason known only to the ML algorithm, to the dangerous. We know that these recommendation systems also drive political polarization. Something that's just starting to happen now is also the emergence of AI tools for altering and augmenting our own subjective reality. Snapchat filters, Facebook filters, deepfakes. And again, these get used for a range of things, from the fun and interesting to the harmful. Deepfakes get used to generate misogynistic revenge pornography. They also get used for advertising. They get used for things, some of which are clearly, if not illegal, right on the border, to things that have commercial value. What this means is that the world we're in is already being influenced in a major way by kind of non-trivial, large-scale AI models that are changing culture. They are changing the culture that we all exist in, and that will have a huge effect. And to just sort of tie it back to what I've been saying earlier, if we're changing culture, we need a large set of people to be able to analyze the things changing culture, because that has a big effect on human civilization. And as it currently stands, these models benefit capital, because capital builds them. Companies build these models and they get to deploy them and they get to make money. It doesn't leave quite as much room for different approaches and different stakeholders to benefit. Obviously, these models have benefits. They're going to be used to help people via therapeutic chatbots. There are going to be better search engines. There are going to be aids to designers and artists. There are going to be amazing tools to help people that are bad at programming, like myself, program better by using natural language interfaces into code models. There's a whole bunch of benefits out here. But because they're funhouse mirrors, they aren't going to by default benefit everyone equally. That's going to take work on our part and work on the part of the academic community. And because these models may cause harm to people that are less represented or represented but stereotyped, we need to be able to develop the tools to let us interrogate that and at least know that that might be happening. So my final point is just, what are some things we can do to make things go well? I think it's all about reducing asymmetries. There is a power asymmetry in model development right now, and I believe it needs to be worked on by broadening the range of actors that can build foundation models. I believe that universities should be building these models either individually or as consortiums. And I think beyond universities, as Percy said, we can look into things like distributed training and big science and other ways of kind of skinning this cat. We also need to deal with the inherent information asymmetries here. There must be more tools available to assess, measure, and analyze foundation models, partly to encourage accountability, partly to discover capabilities in them that we don't yet know exist. And we need to create things like data sets to test for types of benefit and harm. And we need to create, leaderboards that go into some of the societal impact or ethical dimensions of the model, in the same way we have leaderboards that look at raw performance or on reducing a loss curve for something like, superglue. And finally, and this is something that I'll be having some research coming out on soon, is governments should invest in tools to audit, measure, and analyze models that are deployed, because we need to create a shared, accessible set of societal information about these models if we want it to go well. So along with building them, we need to equip government with the tools to see what is being deployed and to sort of be able to automatically analyze and to some extent interrogate these models as they're being placed onto the ecology of the internet. So that's my talk. I think I've got time for some very brief Q&A before we go to the next section. You can reach me on Twitter at jackclarksf. I write a weekly newsletter called Import AI at jack-clark.net. And in the weeks since I said I was doing this talk, I've had a lot of kind of robust discussions with people on Twitter and other places about this. So thank you. It's clear there's a huge amount of interest in this subject from a large set of people. So thanks very much. And I hope that we can do a quick bit of Q&A now.
All right. Thank you, Jack, for that really insightful talk. I really like how you laid bare the academia versus industry research gap and issues with power. So let's do some Q&A. So I wanted to start by asking you a question about incentives within the industry. So there's a big difference between, in terms of resources, between, let's say, a Google and a startup. Mm-hmm. And right now it's kind of hard for a startup to break into the search engine market. So do you think startups will be able to compete in 5 years, and what need to be done right now, even putting academia aside?
Yeah, I think that if you look at things like neural machine translation, that was a system that Google developed and replaced a load of very expensive, specifically developed translation systems at Google. And similarly, these large generative models that are being trained now are incredibly good at doing things like search and other things. So I actually expect that the emergence of these models is going to shake up the game board a bit in terms of dominance in different areas, because once you train these models, and you could imagine sets of startups teaming up to train one and then all using their access to it to compete in different business areas against larger companies, you may be able to change some of the power dynamics a bit. I think that's an opportunity that's out there.
Yeah, great. So now let's talk a little bit about academia. How should we get funding for academia? I'm very curious about this one.
Well, there's the National AI Research Resource, which is being worked on by the OSTP in the US White House. There is an RFI out for that, which expires on October 1st, and they're looking for ideas on what that should look like. We also just passed the Endless Frontiers Act, or as it was renamed, USICA. By we, I mean Americans, not myself. And USICA unlocks something like 200 billion of funding, which we can potentially use to increase funding at places like the National Science Foundation and others. So I think money is actually out there, and what we need to do is develop the payload for the money to go into. And also, just speaking frankly, whenever I go to Washington, because I do a lot of work in policy, I talk mostly about this problem. And I talk mostly about this problem to the US government and say they need to significantly change resourcing here so that academia kind of has an ability to do it. I don't know how effective that is, but it's what I spend a lot of my personal credit on.
Oh, that's great. All right, so unfortunately we have to move on. So let's thank Jack again for that great talk, and we'll chat more about this at the panel.
Thank you.
So now we'll have two 10-minute talks from two Stanford professors whose primary research area is not AI, but whose worlds have been colliding recently with foundation models. So first is Michael Bernstein, an associate professor of computer science at Stanford and member of the HCI group. Michael builds social computing systems involving anywhere from small teams to large crowds to help groups achieve collective goals. He specifically looked at governance in online communities, interactive machine learning, and recently has led the effort at HI to design an ethics and society review board for AI research. Michael, take it away.
All right, thank you very much. So I'm going to talk from the perspective of a human-computer interaction researcher. So this is sort of my day job in some sense. And let's talk about what I'm going to call threshold effects here. So I'm going to tell a story of ancient history to kind of set the stage here. A long, long time ago, hundreds of days ago, it used to be really, really hard for us to make public content on the web. And you had to own a server. You had to figure out how to set up Apache config files. You had to learn this crazy tongue of hypertext markup language. It was a big deal. But over time, tools arose that made it much easier to publish. So you can think of stuff early on like WordPress or MediaWiki, and then eventually Web 2.0, now I can rep my SoundCloud. Things changed. And What happened here is well described by what Brad Myers, Scott Hudson, and Randy Pausch described back in 2000 about this threshold ceiling diagram. I'm going to draw a graph here. On the y-axis is just going to be what I'm going to call threshold, how hard it is to sort of get off the ground to do something. And on the y-axis is going to be the ceiling, which is the sophistication of what you can create with that thing. So early on, you had to basically be fluent in the entire server stack to get anything public on the web. But over time, as Tim Berners-Lee started with the web, we had HTML, which dramatically reduced how challenging it was, the threshold to making a web page. And eventually we started seeing things like Markdown. I can write posts on Medium, or I can just fire off something on Twitter within seconds. And this has dramatically reduced the threshold. Now, it's also changed the ceiling. I can't do anything as expressive on Twitter as I can writing a full stack web app, but that threshold has really dropped from months and months to just a few seconds. Likewise, we had really, really high threshold, high ceiling tools like Adobe Photoshop move into something like Instagram, where you can, again, do pretty complex, but not as complex stuff. Movies, Premiere, moving into something just like TikTok, where I can add filters. I can do it now. So we lowered the threshold. Something went from really hard to get in to relatively easy. And what happens? This is the central question here as it relates to foundation models. What happens when you lower that threshold to publishing? Well, two things. One, you're going to get this massive increase in adoption of the medium, right? A lot more people are tweeting than are making full stack websites. And you also have a really broad proliferation of different kinds of use cases that the original creators probably were not intending or aiming for. Now, this does increase sort of an iteration speed in a sense. This is the very classic human-computer interaction cycle where we have an idea, we implement it, and then we reflect on it. And just like research itself, this praxis of design requires this reflection and iteration. It's this iterative process. And so every time you're lowering the threshold, you're making that implementation easier, more accessible, faster, you're getting more turns around that cycle, which means you get, in principle, better designs. It does mean co-option. So I'm guessing that when we started the web, we were not imagining communities of knitters, but it's pretty cool that we have them. We were not imagining the largest encyclopedia in the history of mankind, of humankind. We were not imagining that Percy could just write tweets and it would go out to the world. At the same time, we were probably also not considering platforms would be used to convene the alt-rights, that there would be hate activity going on online, that there would be cyberbullying, and that all sorts of things were going to happen because people co-opt these platforms in ways that maybe I'm relatively confident that the original creators were not intending or even agreeing with. So we had this entire thing that happened as the threshold lower. And this entire time, though, one thing remains stubbornly high threshold. That's AI. It was incredibly difficult to get going. To really build an AI, you generally required some sort of advanced coursework or an advanced degree, an internship with Andrew Ng, a lot of effort to collect data and to train it. So when we talk about foundation models, I feel like we often put our focus on the fact that the ceiling has gone up, that performance is improving on a series of tasks, that this approach has moved our benchmarks. This is raising the ceiling. But what I want to argue is that I think the real action is going to be on lowering the threshold, because these foundation models have lowered the threshold. The few-shot nature of them, the natural language prompts, basically make it so that all of a sudden, you have people who previously could not or would have required a ton of effort to train an AI start crafting AIs. And we can start to see that there are lots of opportunities here. Certainly, and here I'll point to work by a PhD student, June Park, finding ways that it is possible to help scaffold non-expert users in writing effective prompts. Here's a particular challenging task that GPT-3 doesn't do all that well on. A few-shot learner does barely above chance at trying to predict whether a community is going to moderate a comment. But if we start to decompose these concepts, that people can start to basically take this question and decompose it into a few different questions that are more amenable to GPT-3, all of a sudden we start to, on some tasks, see better F1 scores. So there's a real lever here for human insights. It also means we're going to start seeing a bunch of different kinds of interactions. Now, you'll notice that these citations are actually from before GPT-3. In the bottom left, you can see that the HCI community has basically been working on Codex for the last 5 years. So thanks HCI community. But imagining interactions ranging from being able to use natural language to generate code, to edit an image, to find fashion, to having the ability to automate tasks on your mobile device, to having ubiquitous computing systems that can do some activity recognition, so that, for example, it'll start making your coffee when you wake up. Now, there are going to be all sorts of new forms of interaction, as I'm saying, that we haven't foreseen. For example, emphasizing this prototyping approach. So if we make it faster and easier to prototype, what are we going to see? So maybe we can start to see on the positive side things like social network designers taking advantage of the fact that these foundation models have memorized a bunch of behavior on these social networks, so that they can use a natural language natural language prompt saying something like, well, here's a person who's upset about a breakup, and we can actually see and populate a space with what might happen. I could say that my colleague James sees that post and decides to reply, and these are actual responses generated by GPT-3. So we could actually start to populate these spaces, not just with what might happen in a social space, but also say, here, Trevor decides to be a troll. We could foresee the kinds of negative behaviors that are going to arise before they actually arise. If we can do this, I think we can do a much better job of forestalling some of the negative outcomes on these platforms. We don't have to imagine necessarily what's going to happen. We can essentially simulate some of it and see, you know what? We need to build protections for this kind of thing. But again, I'm going to bring up the but. And here I think I'm beating the drum that the first two speakers really spoke about already. We saw with publishing that when we lowered the threshold, we got many of these positive and creative applications, but also a number of really negative and harmful ones that we were maybe not as a society able to grapple with in advance. So I think we need to say that the same thing is going to happen here. As we lower the threshold, there's going to be co-option, not just of these applications that I think will be, handy, will be useful, and that HCI will be, as a field, really excited to explore. But also, as Percy mentioned, this will become an endless fount of misinformation. It'll become a troll generator that's really difficult to detect. That I can just call up a thing that says, "Hey, this person, I don't like them. They broke up with me," and go mess with them. We can reword articles for higher emotional valence and vitality. So we know that these kinds of articles get spread further on social media. If I can have a thing that makes me sound more viral, hyper curated online profiles, we're going to be able to get feedback, and it's going to make us look a particular way that makes us look good in the way that we want, but then everything starts to feel more fake. Jeff Hancock in the communication department has been thinking a lot about this kind of work. More targeting with less data, right? That's a foundation. Risky routine classifiers. We're seeing things like your insurance rates might start going up because we can classify what you're doing with less information about you. So what and all these things that we probably haven't already foreseen. So what's going to happen here? We're going to see a wide variety of new interactions, both on the positive side, but I think really we want to focus on what are these risks and how can we mitigate those risks? What principles should we be following in the design and deployment, both of the models and of the applications? What should their contract be? And I'm going to sort of hand that question on contracts perhaps off to my colleague Dan Ho, who's going to take the next piece. I wanted to thank students who've been working on this kind of work that I mentioned, my colleague Percy, who's co-advising some of this work, and funders.
All right, thank you, Michael. Love the framing of foundation models reducing the threshold. We'll come back to questions in a bit. Let's go on to our second talk by Dan Ho. So Dan Ho is the Benjamin Scott and Luna M. Scott Professor of Law here at Stanford, a professor of political science and associate director at Stanford High. His scholarship centers on quantitative, empirical, and legal studies, focusing on administrative law and regulatory policy, anti-discrimination law, and courts. So recently, Dan has been really interested in using NLP for legal applications, and his talk will intertwine these two themes. Dan, please take it away.
Well, thanks so much, Percy. I think the work here in bringing this group together has really been quite engaging. I'm going to talk about two topics. One is the use of foundation models for law as an area of application and the potential promise there, but then also the law of foundation models. That is, what are the kinds of legal constraints that may actually affect what kind of foundation can be built? This is going to be admittedly an American US perspective, in part because of my perspective and the perspective of the wonderful collaborators who helped with the white paper, Peter Henderson, Neil Guha, Lucia Zhang, Mark Kras, Julian Nyarko, and Jenny Hong. On the first topic, it's widely acknowledged that while the US legal system strives for justice for all, there are pretty profound issues with access to justice. In 1978, President Carter gave a speech to the American Bar Association that said, quote, "We have the heaviest concentration of lawyers on earth. 90% of our lawyers serve 10% of our population. We are over-lawyered and underrepresented." That situation has not changed much to present day. For instance, look to the systematic underfunding of public defenders, or the file room of one of these adjudicatory agencies that looked something like this just a few years back, where it took about 5 to 7 years for a veteran, for instance, to have an appeal resolved. And one estimate has it that about 7% of veterans pass away while waiting for their appeal to be resolved. And at the same time, one of my colleagues who spent much of her writing talking about access to justice pointed to a kind of less noticed revolution of legal services aimed at America's low and middle income consumers. Technology is replacing lawyers wholesale in areas like preparing wills or forming limited liability corporations. And what we do in the white paper is we spell out a kind of range of different applications across the stages of a civil lawsuit. We'll note that that's already quite prevalent in areas like discovery, which is the process where by litigants seek to find facts, and the kind of conventional way in which that was done was, for instance, by providing these large bankers' boxes of files. And that process has been revolutionized already by the use of natural language processing. That said, one of the historic challenges in terms of thinking about even applying these kinds of tools to law is that labels are really expensive. The law has not had anything like the kind of large-scale benchmark data sets that have powered sort of NLP development. And so the basic question, the basic structural challenge is that law is expensive. It's hard to hire lawyers to label legal decisions. And one of our graduates, Pablo Arredondo, figured out that actually there is a place where we can look for high fidelity labels of legal decision, which is that lawyers have actually come up with extremely complex sets of rules about how to cite prior precedent. And one of those rules turns out to be about the use of particular parentheticals that literally states in the Blue Book the conditions, grammar, and how to characterize holdings of prior court decisions. And holdings are this kind of basic task in the first year of law school. It's the part of the judicial decision in a common law system that can be relied upon as precedent to cite to. And so what we did is we did some work here, basically leveraging this really detailed set of rules to extract these kinds of holding statements out of existing case law. The context may look like the blue. Then there are the purple kind of legal citations. And the holding statement is something stated in that parenthetical that characterizes the key precedential value of prior cases. And then it turns out we can actually construct something like one of the classic Q&A tasks, where we can find very similar holding statements here about qualified immunity for police officers and turn that into a kind of question and answer task. And here's where we start to see some of the promise of foundation models for the law. Foundation models boost performance pretty significantly on F1. And what we then did is actually compile through the Harvard Case Law Access Corpus kind of 3.4 4 million federal and state court decisions and do some domain-specific pre-training. One sort of important thing here is to really create. We found was really important to create custom vocabulary and sentence segmentation that paid attention to that complex system of legal citation, and that turned out to actually perform best. And that's where you see some of these really interesting potential gains, where the gains from domain-specific pre-training and these foundation models seems to be largest when the training data set is smallest. That said, we have a long way to go. An example offered by Julian Nyarko is about GPT-3 and its limits in discerning legal reasoning. So a simple prompt might be, are liquidated damages clauses enforceable? Liquidated damages typically appear in contracts to specify what the damages are if a breach of contract occurs. And it is absolutely the case that GPT-3 can parrot what the black letter legal statement is. Liquidated damages are generally enforceable unless the sum stipulated is exorbitant or unconscionable. But if you feed GPT-3 anything like the kind of fact pattern that we train our first year law students on, like the contract over a Toyota Corolla, where the liquidated damages are posited to be $1 million, GPT-3 is not able to actually perform that simple form of legal reasoning, nor is it able to do so even if you specifically state that $1 million is exorbitant or unconscionable. So there's a long way to go, which leads me to the way in which the law may actually constrain the construction of foundation models, given all of the basic questions that Percy and Jack covered so well about the performance, bias, and mechanism of these kinds of models. And I'll only scratch the surface here, but I'll highlight a few. One is obviously the worries about the extent to which foundation models may bake in bias and lead to disparate treatment or disparate impact. Another is the questions about due process when used within any kind of decision-making system, where due process doctrine typically requires a sufficient process when an adverse decision is made. And as Danielle Citron wrote in a kind of logical AI-based system, there were computer programmers encoding benefits decisions that actually violated the federal regulations on this. And that becomes, of course, much harder to audit when we're talking about the kinds of decisions that may be embedded in more opaque foundation models. Then second, there are questions about input liability. Percy noted that he didn't want his vacation pictures used. Think here of GitHub Copilot, the machine learning-based programming assistant, and there are basic questions about the licensing terms and fair use. To the extent that Copilot is trained on data that is not, for instance, on GitHub. And the kind of biggest tension here lies in big questions about accountability. It was only this past term that in the Van Buren case, the Supreme Court actually pared down an interpretation of the Computer Fraud and Abuse Act that actually could have criminalized a lot of web scraping conduct to bring data into these models, and if you were violating the stated terms of service of a particular website. And that obviously had major implications. Facebook was involved in one of the kind of underlying CFAA cases in terms of the ability to actually access this kind of data. Last, we also spell out the fact that there may be protections for model or inference outputs from these kinds of models. But at the same time, while there may be legal protections, the interesting thing from kind of the perspective of law is that it may actually challenge some core tenets of legal doctrine itself. So colleagues Tony Massaro, Helen Norton, and Margot Kaminsky wrote a really fascinating piece arguing that, quote, if we take the logic of current First Amendment jurisprudence and theory to its natural conclusion, MS Tay, which was the 2016 chatbot that was taken off of Twitter after 16 hours due to inflammatory tweets that described by one newspaper as, quote, artificial intelligence at its very worst, MST may actually have First Amendment rights under current First Amendment doctrine. And that is, of course, something that may not just affect foundation models, but it's also the kind of cross-fertilization that I think is so overdue, because it may be an area where the emergence of foundation models may actually be really teaching us something about some of the limitations of current legal doctrine and inspire a significant amount of rethinking. Thank you. With that, I think we'll turn it to Q&A.
All right, thanks, Dan. And now we will go to Q&A. Can't seem to turn on my video anymore, but that's okay. Let's see. If we're talking about building foundation models for law, Michael talked about lowering the barrier of entry, lowering the threshold. There's also a barrier to entry for law. For example, I can't really read legalese. How do these two types of barriers interact with each other? And maybe this is a question either of you could speak to.
Yeah, I'm happy to take a first stab at that. I think we did this other report where we tried to understand how it is that government agencies were really experimenting with forms of AI. And one of the kind of themes coming out of that report is that while nearly half of federal agencies, for instance, are trying to do this, the best use cases really came where you had core staff members within those teams that both had technical insights and deep domain knowledge. In the Social Security Administration, for instance, they built out a sort of NLP system, and it was really built out by some of the folks who were adjudicators for several years and figured out what kinds of tools they really wanted built for themselves in the process of adjudication, which I think exemplifies some of the sort of interesting HCI components of this. But Michael, I'd be curious for your perspective on it.
Yeah, it's interesting. One of the first things I got asked from someone in the government to do when I started working on crowdsourcing was to help them crowdsource more interpretable versions of public legal documents and policies. I think we have to differentiate here. There's sort of what's internally needed for the legal policy to be correct, and then there's what's projected and clear to sort of the citizens, and those may be very different in the same sense of like how I would teach how machine learning works to someone who's just learning is going to be different than the kind of conversation you would have with someone who's an expert. And so I feel like that needs supervision that doesn't exist. We can't just sort of say, oh, here we go, because if we just try to translate what's already there, it's going to try to take stuff that might be, as you suggested, like quite sort of technically complicated legal detail and make it simple, but in a way that's not right or gives the wrong intuition. I'm, in some sense, almost more interested in how it might help go the other direction, that if I can provide there's this vocabulary gap. If I don't have the words to describe what I need to know or the kinds of legal policies I need, like help me get in touch with experts who can help me, just help me cross that chasm.
Right. Thanks, Michael. We have another question on, both of you discussed the risk and co-option of these models. So how should we reason about these risks, and what recourse should we take to proactively and reactively mitigate them?
I want Dan to go first on this one.
Well, I think part of the reason why I split up my portion of the talk to both be about the application portion and also an understanding of the legal constraints is that a lot of the times the way we choose to do this as a society is to take broad ethical principles and then write them down into law. And so some of the ways in which we obviously do risk mitigation has to actually involve writing enforceable rules rather than merely sort of hortatory ethical principles. And so, I was very interested, for instance, in what Jack noted, which is how do we actually build workable kind of audit system. And I think, Percy, I think you made a really compelling case that academic auditing is part of that. But I would also probably say that alone is not enough, that there may have to be actual enforceable rules to be able to audit systems, for instance, that might be used for benefits adjudication to make sure that they're actually designed and work in a way that is legally compliant.
Yeah, what I'm wrestling with here is, in computing, there's a real push for CS for all, right? To try and lower that threshold, to give as many people as possible access here. And yet in some, in other domains, that's not necessarily the case. We have licensing procedures, we have communities of practice where groups will self-adjudicate, right? So medicine, law, and others, where there are real consequences. You're barred from practicing if you have a severe ethical violation. And so I'm wondering, at what point are these tools? No one says medicine is bad for you or that it can't be used poorly, but at what point do we need to start asking more seriously about those kinds of professional associations and what that would mean, and what harms it would do to create that in terms of restricting access to potentially marginalized groups versus the benefits of say cutting out negative use cases. That's really what I'm chewing on. Is where do we stand on that?
Yeah, just to follow up on that, I mean, in your talk, you talk about the co-option of publishing, which I guess we've seen kind of play out. Are there any lessons there that we might be able to take and apply them to foundation models?
One thing I can say is I was early on, I think, more optimistic about the role that sort of design and research could play in sort of setting models and think of it as a role model or a path forward. Look, we should be doing it this way. I think I've become far more cynical over the last, say, 5 years, maybe more in line with Jack, that while we can show pro-social paths, there's nothing that prevents an antisocial actor from taking that and just ignoring it or doing the opposite. And so in general, my sense, and Dan would be the expert here, my sense is that policy tends to be reactive rather than sort of happening before the issues are, before there's a violation. But to the extent that we as a community can do something like what the researchers did in CRISPR, where they came up with essentially a set of principles that they published alongside the technique and say, here's what we think is okay and here's what we think is a violation. I think that's fairly counter-normative behavior for computer scientists, but I think it would be a really important step if we could, say in this group or elsewhere, convene civil society, researchers, industry, and so on, and say, this is what is okay, this is what's not. And then there becomes at least social disapprobation for that kind of behavior.
Yeah, we definitely need some more professional norms here. All right, thank you both for your talk and taking the questions. So this concludes the talks, and now we're going to move on to our first panel discussion. So let me introduce the panelists. The first panelist is Jack Clark, so please welcome him back. Next, we have Su-Lin Blodgett. She's a postdoc researcher at Microsoft in the FATE group. She studies social implications of language technologies, and she's recently led some really nice critical work on how to think about bias and how to measure it in NLP. Next, we have Eric Horwitz. He's a technical fellow and the chief science officer at Microsoft. He's led efforts at the intersection of technology, people, and society. He has made foundational contributions to principles for responsible and ethical AI, and has always been a strong advocate for human-AI complementarity. Next, we have Joelle Pineau. She's a co-managing director at Facebook AI Research and associate professor at computer science at McGill. She has worked on planning in partially observable domains, dialogue systems, robotic assistants, and she's led some really remarkable reproducibility efforts in the machine learning community for the last few years, such as the Reproducibility Challenge and the Reproducibility Checklist. And finally, we have Jacob Steinhardt. Jacob is an assistant professor of statistics at UC Berkeley, He works on making machine learning more robust and aligned with human values. Recently, he and his group have built several challenging benchmarks for language models across different domains like language and code. All right, so welcome all of you, and let's get started. So as is advertised in the name of the panel, I want to start with two broad questions, one on opportunities and one on risks. So the first one is, what are these applications or sectors do you think are most going to be transformed by foundation models in the next 2 years, even based on kind of the current trajectory? What are these types of applications or types of interactions that we haven't seen? We need a bit of imagination, don't exist yet, but are now made possible. Maybe we could start with maybe Joel and Eric, since they being at Facebook and Microsoft have seen a lot of resources invested in kind of applications of foundation models, and then we can go to others. So maybe Joel, you can go first.
I can start a bit. I mean, I think, there's definitely tremendous potential that goes across all sectors. So it's a little bit hard to pick which ones is the most promising one right now, to be frank with you. I think the report put out recently does a great job at highlighting a few of them: education, healthcare, law as being prime examples. But I think it could have just as much talked about some of the potential in transportation, some of what we're seeing, not just in smart vehicles, but across the whole realm of the transportation industry, some of what's happening across finance and that industry as well. And finally, I will mention, I think creativity, entertainment, all of this ability to really harness the work that's been done on generative models of AI and use that to enhance human creativity in really significant ways, I think is incredibly exciting and really promising.
Yeah, the ability to generate is definitely something that's kind of jumps out at you. Eric, do you have anything to add to that?
Yeah, sure. I mean, my sense is that the scale of the data compute and the model capacity that's been enabled by the unsupervised learning methodologies has really led to both advances in representation and generation, per Joel's comments. So I'm excited about the possibilities of how these technologies will change the lives of people within their professions as well as in daily life. I see really incredible boosts in language tasks, visual tasks, and generative tasks. I think they'll be continuing to see surprises. And so I see, let's say for consumer and business technologies, I think the texture will change, for example, when it comes to multi-step interactions, not just one-shot recommendations or recognitions, but rich interactive dialogue where multiple topics and goals will be maintained, and there'll be a pushing and popping of a kind of a stack of interrelated threads, and having a conversation with AI technologies versus having these one-shot experiences. I also think that there'll be changes in the course of daily life when it comes to extreme personalization, where we've seen that it takes quite a bit of common sense for systems to help us understand and guide us on how we spend our time, how we collaborate and get things done. And we're seeing some great directions on that front. Already some of these services are being offered in our Office product line, for example, in Dynamics. On this engineering front, there's been some well-deserved excitement with software development, and we can go much further. I think there's impressive engagement we're seeing in the private preview with Copilot. And so I think that'll be a game changer in some ways for software development. Healthcare, one particular area that I've been looking at is scientific discovery. I think we're going to see platform models or foundation models for molecular simulation to change chemistry and biology and physics in fundamental ways, to speed up our ability to understand what molecules do when they interact by many orders of magnitude. We're seeing signs of that coming our way. And with the recent work in biosciences with UniRep and ESM1B, these pre-trained platforms, embeddings for understanding proteins, not just structure, but function, I think will be game changers for science coming our way.
Great, yeah. Science is one of the applications we maybe think less about, but I think it's really exciting as well. Maybe, Jack, did you want to?
Just want to do a really quick shout out for really intuitive search in very specific domains. Like, because you can generate stuff in a domain, it makes it easier to do things like find recommendations for similar scientific papers if you start to like use these models in the right way. And so I think that we'll use them to sort of change how we educate ourselves, at least at the level of like when you're beginning to read about something. I think these models will give you better and more intuitive recommendations than a standard search engine.
Cool. Maybe we could talk a little bit about the flip side. I think all of this sounds great. There are, as many speakers have commented on, many risks associated with foundation models. What are the ones that you think are kind of most to be worried about? Are they the short-term risks because these models are already out and about, or are they kind of longer term because the future is so unpredictable? And what kind of action should we take? So maybe Su-Lin, we can start with you since you've thought a lot about social bias in NLP models, which is very, pertinent here, has come up a lot of times.
Yeah, thanks. I have a lot of feelings about this, so I might have a somewhat long answer, if that's okay. I am the resident skeptic, so I'm going to be appropriately skeptical. So I think I worry about a lot of harms, but I know all of them is not like a very useful answer. So I think I'll say that maybe the thing that worries me the most is the rapid entrenchment of these models. So the view of these models as inevitable or an unmitigated good. I think it's a really risky frame because it forecloses research into alternatives and it assumes that development and deployment of these models must happen, which forecloses situations where we just say, hey, the risks or harms really do seem to outweigh the benefits. Let's not use this. And also ignores the fact that there are already lots of communities that don't want this, right? Communities for whom these kinds of models mean increased surveillance, or there are cultural resources made available for general cultural consumption and appropriation, or commercialization of their cultural resources for which they get no benefit. So for me, one risk that kind of generates maybe all these other things is that once widely deployed, these models will inevitably cause the kinds of harms that people have talked about, and it'll be very difficult to roll them back. I think this rapid entrenchment really concerns me in particular because we hardly know what these harms even will look like or how they emerge. The evaluation paradigms for these models tend to involve measurements over a model's internal representations or evaluations on some constructed benchmarks, but they tell us very little about how harms actually emerge in deployment. In fact, we don't even really know how much or how little these evaluations tell us at all. So I think for my part, I guess I can think of a few things that would help. First is knowledge of which use cases these models are adapted to, which is to say what these models are purchased for and when they're sold as products. So we could at least meaningfully research likely failure modes. But that's information that's unlikely to become available to academics or other potentially critical actors. I think similarly, industry practice often departs significantly from academic practice. For example, these models are part of very complicated pipelines with lots of moving parts. And I think academics and the public generally know relatively little about what these pipelines look like, what interventions are available to industry practitioners for measuring and mitigating harm, what ideas about language of people shape these decisions, what constraints do they experience. I think we know very little about how the technologies that people experience are actually produced, and we ought to support work that tries to uncover this. I also think another direction that we might consider supporting are efforts to uncover how technologies are actually experienced in their deployment settings, right? So this would be context-specific, localized efforts, things that involve interviews and community workshops and other approaches, which are labor and time intensive and ought to also involve the people who experience these technologies. But this is also the kind of deep work that is not often rewarded in computer science. So I guess, I don't know if did you already ask, what to do, how to move forward? Do you want me to say something about that?
Yes. Or these are all really good points. If you have any solutions, I'd love to hear them.
No, obviously nobody has solutions, right? Except I think first to reward this kind of work, the work we want to see, right? So in computer science, make it acceptable to publish about this kind of deep kind of case study work and community-oriented work. And also, not all this work should happen in computer scientists and, technologists we need to get good at decentering ourselves. So also fund social scientists and humanists who are already doing this work and have been for a long time. I think as others have said, I think quite rightly already, stop framing these models as inevitable, as though the historical trajectory of AI is one that just has to culminate in these models, and stop valorizing scale, right, as an unmitigated good. From my perspective, I think just, like my one-liner maybe to summarize all this is that given that we don't even know what the harms of these technologies will be, it's just absurd to assume that those harms will be outweighed by the benefits.
Yeah, these are really good points. And I think that inevitability question has come up a few times, and maybe we could drill down into that a little bit. There are many levels at which we should kind of reject the inevitability, right? There's the models, or even the collection of data at large scale, or the use of machine learning. So at what level is the kind of the right place to say basically stop, and we should consider all kind of alternatives?
Can I do a quick point on that? So maybe just to build on Sue's point and also respond to Percy's thing. These models are like being deployed into an ecology that we all live in. And previous times we've deployed new stuff into the ecology we all live in, we've like melted the ice caps and broken the planet. So I do think that there's work to be done on monitoring like what happens as we inject new text and new code and new outputs of these models into the internet around us. Like, how is it changing the environment that we all exist in, and actually in a real sense the commons that everyone needs to use to train things. And additionally, I think that bound up in that is building auditing systems to kind of look at models that are being deployed at scale and try and understand, as sort of Sue said, both at the local level, but at a more macro level, are there harms being generated? We saw this with facial recognition systems that got deployed, which had unequal performance for different people. And we only discovered that through third-party auditing by, the Gender Shades project, and that was subsequently baked into NIST's facial recognition vendor evaluation. So I think that there's work on auditing that we need to do to actually establish things like harm, and then understand, are there things that shouldn't be done, or are there things which we need to reassess the deployment of?
I'll just make a comment that I really appreciated the discussion from Sue Lin and Jack and so on. I'd like to ask the question of this, maybe the panel, to extend, like, these questions are central in everything from logistic regression being applied to the large scale platform models of the fine tuning paradigm. And maybe today I thought we'd focus on like what's different or new about going into these large scale neural models versus having an ongoing discussion, which these aren't resolved issues. And many of the issues that have come up earlier are still very applicable, of course. But with the large scale models, what comes to mind is we have more power now. We have issues around, when I say more power, I talk about the generative power of generating really high fidelity audiovisual content for disinformation campaigns, which even raised the stakes of what it means to mitigate that kind of thing in our society, what it means. New approaches to powerful psychological operations that can convince and persuade and manipulate on a new kind of level. More powerful uses of AI, like in the coding. So the coding example and engineering example is now we're actually seeing these models being used even for more direct effect in the world, creating artifacts that are taking action in the world that might not be safe, or that might create new kinds of risks that we hadn't thought about before, because we haven't had models in the past that have been generating in a compelling way snippets or even larger pieces of code that might be integrated into programs. And so at the same time, the larger models are more inscrutable. And so we have new techniques and people wrestling with checklists and stochastic probes, for example, that might require new kinds of technologies and methods to even probe and understand the behavior of these models. So I see many of the issues and questions that have come up in the past over the last decade just being in some ways amplified, but some new ones coming to the fore. Like who would have thought about, 12 years ago, safety risks with recommended code snippets?
Cool. Can I say something, Percy? Or?
Go ahead, Jacob.
Yeah, I mean, I like all these framings so far, and I think all of the risks discussed so far are important. I wanted to, there's kind of one frame I like to think in terms of, which is kind of, what things should we expect to get worse as models become more powerful and more capable? And I think, I like this Foundations Models workshop because I think it kind of pushes us to think along those lines. For me, one big one is what I call misalignment. So this is sort of the pursuit of wrong goals. Things that maybe look good according to whatever objective you wrote down, or maybe that are good according to the measurements that you can take, rather than things that actually are good. And so I guess maybe that puts me in the long-term risks category, because I think, this is one where the more powerful the AI gets, the more it can sort of exploit these differences. I think Chris Ray, I don't know if he's here today, but he had some interesting work on sort of identifying hidden strata in data where kind of as you make models better on average, they actually kind of exploit like incorrect patterns on these hidden strata. And so there's, subgroups of the data where you're doing worse. I think there's also, a lot of other work showing this where you kind of make models bigger, they might do better on the objective you wrote down, but they'll do worse on other objectives. So I guess that's one single thing that feels, I guess, most underappreciated to me. But more generally, I think, I think we're just going to see very rapid technological and societal change. And I think it'll happen faster than most people expect. And it's going to be hard to predict exactly what those changes will be in advance, just from trend extrapolation, because of this point that Percy brought up on kind of emergent behavior. So kind of the big question on my mind is, how do we prepare for this? I don't have great answers, but I think we should at least, as a community, be spending a lot of time brainstorming and discussing possible future risks, scanning for new emergent capabilities that might show up that could precipitate those risks, and kind of work proactively on mitigating things before they occur rather than after they occur. I think maybe cyber security is one example there where we might want to be doing a lot of work in advance. And then something that I think will just help across the board, both short-term and long-term, it's sort of already been discussed, but more auditing. We should just be kind of measuring everything we can in as many contexts as we can to kind of try to find issues. And I think another thing along those lines that is maybe a bit less appreciated is something I've been calling counter-auditing, which is we should also, there should be a red team that's intentionally creating kind of, things in the lab that have problems and making sure that the audits that we're generating actually find those problems, right? So that we know that we can trust them. So I think those are all of my thoughts, but I really appreciate all of the other discussion as well.
Great. I wanted to talk a little bit about...
Can I say something?
Oh, go ahead.
Percy, really quickly. And it's something I want to pose to the panel that because I'm really interested in people's thoughts on this, is one thing that I've kind of observed in thinking about kind of risks of these systems, which I think is, as Eric rightly pointed out, extend to just many systems generally, not just foundation models, but is that a lot of the kind of high risk settings or the riskiest settings that we've identified where these systems are deployed are very disconnected from academic research, and they're often not uncovered by academic research, right? Like the places we hear about them are through journalistic efforts or things like this. So I'm thinking, for example, of like US immigration officials using kind of like NLP technologies to vet social media, like profiles of immigrants or refugees, or medical settings or things like this. And I guess my question is like, so not all of these things are underpinned by foundation models, these kinds of models yet, right? But I think it's not too wild to imagine that they might be. And so I guess, the NLP research community isn't maybe developing these directly. We maybe don't have a lot to say about these. We don't talk about these at our conferences, but how do we make it so that we are not disconnected or unaware, right? How can we make it so that it is not just journalists who are uncovering like the kind of uses and abuses of these technologies, right? How do we, as a community, have something to say about these? It was just something that occurred to me when I was so startled that these things would be used in immigration settings. Right? I was like, how can this be? How do we not know?
Yeah, one direction, Sulin, I'll mention is that, and this came from my service as commissioner on the National Security Commission on AI that just filed a report in March, is that we need to basically come up with regulatory activity. And we have had Congress leaning in for recommendations that came from that committee and other places that requires disclosure and metrics and maintenance policies when it comes to various AI technologies used by government agencies. So it's not just journalists digging to uncover the way things are being done, but actually to have best practices and requirements for disclosure to the public. That should help, I think. And we see some really great moves on that front right now.
Yeah, so Lynn brings up a really good point. It relates to something I was going to ask about. As she pointed out, industry practice is very different, right? In academia, you have these papers on these models and you're studying the bias of them, but the actual social harms are, as Sulin pointed out. So what are things that we can do to kind of bridge the gap in terms of helping researchers become more aware of how these technologies are actually deployed? Sulin mentioned complex pipelines, which those of you who have worked in industry know that it's not just you train a model and you deploy it. It's much more complex than that. And I think one of the challenges seems to be that we have a conversation about foundation models, and its power stems from the fact that it's a general purpose thing. So how do you reason about this object when really you need to be thinking about all the myriad, perhaps infinite number of possible downstream applications?
So maybe just a quick thing, Percy, if I could
go.
One thing that we did at OpenAI and we do at Anthropic is we just use a lot of eval suites because you're trying to characterize this very complex surface of your large model. And so when you have eval suites for things like WinOgenda or things like StereoSet or a whole variety of these ones being developed to assess things like bias or stereotypes or whatever, we use those as well because it all helps us characterize the kind of surface of these things. So I do think that the more academia can develop evaluation suites, the more that will definitely get used in the private sector, even if it's not necessarily published on. And maybe there's a way to bridge that into government and to eventually say, these are some evaluation suites which are kind of broadly used. You may wish to start auditing deployed systems using these eval suites as well.
Yeah, I do. Yeah, eval suites are, I think, great. I wonder how they will be able to capture the kind of deployment. For example, you might evaluate how toxic or biased something is, but these models might have a toxicity filter, or they might be adapted in some other way through some complicated pipeline that it's hard to understand. So does that need to be taken into account, or can a more pure kind of academic metric actually capture the true complexities?
Could I give an example of something that I think wouldn't be captured by this that feels pretty important to me? So I think you could. So I guess the example I have in mind is, let's suppose you have something that's deciding to recommend what news articles to show someone. And it's, just got slightly more likely to rank something above something else that uses like more emotionally charged language. Maybe you'll find that in an eval suite. It's not super clear to me, but once you deploy that, that means that you're creating a pretty consistent incentive for news organizations to use more emotionally charged language in their articles, and that's going to increase polarization. And you can only kind of see that once you have this whole feedback cycle of deployment. So I don't know what to do about that, but it feels like an important case where you're kind of missing stuff in the lab.
Yeah, that's a great example.
I think the elephant in the room. Sorry, the elephant in the room, I think, is how can there be a broader sharing, whether it's complex pipelines or large scale neural models that are being used as platforms in industry to connect with academic research more broadly. And I think that we have to really think deeply about private-public partnerships, corporate academic engagements, so that we can democratize not just the use of these technologies, but the analysis and sharing the results of the analysis, whether it be on the artifact itself or on the larger ecosystem or on the implications downstream in broad ways. Several of us in the corporate space are engaging with some of the funding agencies on ideas on this, like what can we do to share out data sets on usage, for example, to have broader sets of eyes on the potential directions for the power as well as mitigations when it's costly or risky in terms of behaviors.
Yeah. Joel, do you want to say something?
Thanks. I wanted to challenge a little bit the question of whether universities should be playing this role, right? In a sense, I think we've seen this in several other industries, that there needs to be a body that plays a regulatory role, both in terms of like being the watchdog, in terms of setting the standards and holding people accountable for this. I'm not sure universities are in the best place to do that. I think they're doing it by default now because of the speed at which the technology is emerging. But I think we need a longer term solution about who's going to own that responsibility for society, at what level is it going to be, and how is that going to be administered. And so I think that needs a significant amount of thought and leadership to establish. Right now it's happening in a little bit of a piecemeal way, but that's one place where we're just going to need to mature significantly over the next few years. And usually that's done in combination by talking to all the various stakeholders that hold a piece of the puzzle, whether it is the industry, whether it is the academia, the government, the society and individuals and so on. So that definitely needs to happen. The other piece I want to raise with respect to that question is, given the velocity at which the field is moving, that body needs to be have an ability to react and to adapt very quickly. So we're not going to come up with a set of standards that will be the one that will carry us for the next 20 or 30 years, right? There needs to be a very tight loop to some degree to some of the things that Jacob was saying earlier. We need to have a way to adapt this in a dynamic way that responds to what we're seeing in terms of the evidence. And maybe this is one of the challenges, because usually when you set up these organizations, they have a lot of, they don't necessarily function in such a dynamic way, which makes it challenging. The one thing that I would say concerns me quite a bit about these models to some degree, these foundation model, as we call them, is almost their permanence, right? The ability to, or the thought that there would be an object that we call so foundational and that we always adapt with respect to that foundation model. And I think that can be quite dangerous to crystallize on these models so early when we still have so much to learn.
Yeah, I like the idea of a regulatory role. Maybe we can do an experiment. Suppose for a second, I appoint you as dictator, members of this regulatory role. And now we're going to decide, how should we regulate these models? When should we stop building? What application should we completely prohibit? Anyone want to take a stab?
Let me just say, I don't think that there will be general answers, nor, Joel, will there be a general single point of deliberation and reflection and regulation when it comes to technologies. It's going to come from case-based analyses in sectors, I think, largely. For example, when it comes to generative models for generating potentially synthetic media that's fraudulent or that spoofs people with identity, there could very well be regulations. There already are in some countries, and laws about the ability to do that, and the legality of doing that when it comes to generation of content. Same with surveillance technologies.
You're arguing that we shouldn't regulate at the foundation models level, but regulate at the applications level.
I might want to think more deeply about your assertion of what I believe, Percy. But let me just say that the most constructive conversations I've seen so far come from specific examples, usually application-centric reflection and discussion, and then trying to generalize from that across to where else it might apply, that kind of regulation, and what office it might apply to when it comes to Joel's comment about who's in charge and who oversees it. There's probably not going to be an office of AI technology, but in the United States government, but more like the Department of Transportation or the National Highway Safety Transportation Administration that thinks through details of the applications of AI and what to be regulated per sector.
So just to push on that, so we've seen a lot of applications, and if you have various experiences in your roles, how can we generalize what we've seen? Are there any sort of general regulations or principles that we should abide to? Because I think one of the dangers is that when people are building this technology in a centralized place, you're detached from the possibilities, so you don't even maybe think about the harms. So we kind of have to perhaps be extra cautious when we're building these, the foundation, so to speak. So
Yeah.
Any thoughts on what we should be doing?
I mean, I see generalization and requirements and regulations being effective when it comes to transparency. For example, publishing metrics, with the right kind of agreed upon grain size of the analysis, maybe not averages, but looking at error analysis in more detail. The notion of transparency about the capabilities of a system per what's understood about the system and limitations of both in capabilities as well as what we understand about the capabilities I think these should be requirements when it comes to systems.
Yeah. So Su-Lin, you talked about the concrete applications that you've seen. So is there anything generalizable there that we can take away? Or are you advocating?
I'd have to think a little longer about this. I did want to point out though that I think what is hard and interesting about this is that a lot, and this is borrowing a point that Solon Broca's I think has made a number of times, is that a lot of the harms, thinking from a language perspective, a lot of the harms we might be concerned about are not really the harms the law has much to say about, right? Things like stereotyping or the erasure of minoritized language varieties or perspectives, or being impeded from being able to participate more fully in public discourse on like a social media platform, right? Compared to allocational harms like hiring, for example, or credit or things like that. I think these are the kinds of things that we should be reasonably concerned about, that the law actually doesn't help, where the law doesn't actually help us very much, because the law doesn't have much to say about these things. On the question of on the question of like, are there settings where there should be like regulation, as in like do not use? I think, yeah, I mean, I think that the failure modes of these models currently they fail a lot, and they fail in ways that we don't realize, where we don't even realize that they're failing, right? Because their very nature is to produce kind of like very convincing or realistic language. So I think there are many, many applications where that kind of such systems are just unacceptable and should be unacceptable for a long time. So I think of a lot of kind of like higher sort of allocational settings, medical settings, immigration settings, hiring settings, loans applications, and the like. Yeah, I have more thoughts that are not really about regulation specifically. So I'll stop.
Okay. Anyone else want to add something, Jacob or Jack?
I just wanted to kind of echo a point Joel made that I thought was really important, which was kind of this point about permanence. I really liked that. I think it kind of poses some challenges to regulation compared to other risky technologies, right? For something like nuclear weapons or synthetic biology, there's kind of like this single discrete target of like, you don't want an explosion or you don't want an engineered virus. You kind of like know what restrictions to create for that. And you can kind of just say, okay, we like don't want any bad actor to like ever have this like discrete bad capability. But I think we should expect AI to produce new capabilities more gradually. It will already be highly entrenched in lots of systems at the point where a new risk emerges. And so I think we just need to kind of think about that. Maybe we should be creating like, some list of like kind of like fire alarms of like, if this type of, bad thing happens, then there should be, significantly higher scrutiny. But we need to think of that in the context of a place where there's already a lot of stuff deployed. and potentially it needs to be rolled back. I don't know, but like I think kind of it will be out there.
This is slightly pre-regulation, but one thing about the AI industry that's interesting is that it is very legible in that you can read a lot of research on arXiv and you can get a sense of where certain things are going. And what we've seen so far is a lot of regulators, like say the National Institute for Standards and Technology, NIST, want to be helping us sort of analyze and determine what's going on in this space, but haven't really been cued to rapid developments. NIST is focusing a lot on computer vision and facial recognition. We're spending the entirety of this workshop talking about big NLP-oriented models, and we need to somehow help entities like NIST be much more aware, much more quickly that these changes are occurring so that they can at least develop some capacity to analyze this space. So that's an intervention which is kind of simple to make, but one which we probably should figure out ways to do.
Yeah. I want to turn the discussion to kind of the issue of openness and accessibility. So both Jack and I made a argument for increasing accessibility with the hope that if you diversify the set of people involved in the conversation, at least you can hopefully make a better decision. But just to be a little bit critical here, will this really address kind of the power asymmetries, or will the entrenchment and the companies will still be able to still have a sizable gap no matter how hard you try to open things up? Or maybe on the other hand, there could be now a lot of smaller bad actors who kind of mess up the ecosystem. So how do we think about openness and accessibility? I think we want to be cautious and not just universally say that it's a good thing without thinking about it.
I can get us started on this, Percy. I think the simple way to think about it is it's necessary but not sufficient, right? It's an absolutely necessary step towards having more empowerment of, different stakeholders, different users of the technology, startups, university researchers, and so on. But it's not going to be enough. There needs to be something else that enables them to come at the table as a full participant to that. Some of this is access, perhaps, to joint infrastructure for doing this. We've seen it in the other science, physics, for example, the development of government-funded or consortium-funded large-scale infrastructure that really is a game changer in the ability of different participants to participate. And what we see out of that, taking some of the work on physics as an example, is also that the discoveries become the joint work of several actors. You see these papers coming out with hundreds of different authors from all sorts of different institutions. We haven't moved to that stage yet, but I think we need to be really thoughtful about how we get there and how we leverage the contributions that industry is willing to make towards this, because there is an economic advantage for them to do it, but draw them into a way that is much more inclusive of participation of everyone else.
Yeah, to add to Joel's comment, I completely agree. I think certainly on lowering the barrier to entry and coming to the table as equals, we definitely, it's in the world's benefit as well as to the benefit of industry to get more mind share into collaboration on large scale neural models, including foundation models. To bring multi-party stakeholders team to look at some of these issues and so on. Just to connect discussions, this whole idea of models as platforms, data, tools, and compute should absolutely be a key consideration in the current discussion going on right now with leaders at key computer science funding agencies, as well as with the public, on the scope and nature of funding a national AI computing resource. We talk about the computing resource quite abstractly, but it's probably to come down to several ways of thinking about what that would mean. One being this general background compute. We want to support the construction of large-scale models, particularly back to Joel's comment. Maybe this is like the large-scale Hadron Collider model, where we all get together as a community, multi-party, and say we need this kind of model to be constructed with government funds, for example, maybe public-private investment on directions there. It's also important to keep in mind that I know this is a workshop on foundation models, and there has been the rise of this paradigm of large-scale neural models being used as platforms of the fine-tuning paradigm. But we're seeing now the fact the borders and edges are kind of morphing as we speak in terms of what does it mean to have a platform model? Are there families with gigantic augmentation with specific data sets that are used not in fine-tuning, but in a specific family of applications? So I think we're going to see even the whole concept of what a platform model or foundation model is evolving over time. And that will change the way we collaborate and the kinds of funds we need and the kinds of government support academics need and the kind of public-private partnerships and the research we do together will be like.
So I want to ask Su-Lin, so suppose magically the National Research Cloud exists and universities all over the country or the world are able to train models, maybe not as large as the big tech companies, but much larger than we are. Does that address any of your concerns about marginalized populations?
No, I don't think so, because it still presupposes that these things should exist. I think, I'm going to, true to form, I'm going to strike another cautionary note here. I think one thing that occurred to me is you personally were asking about kind of access and people were talking about kind of developing partnerships and all these kind of important things. While I'm largely, very on board with thinking about how to increase access and about these things, I also kind of, a lot of people have noticed in the last couple of years, this tendency towards kind of thinking about, participatory, right, like approaches in machine learning and AI, and participatory whatever has become something of like I don't know what the right word is exactly, has become very popular in AI machine learning. I see it kind of creeping into NLP also. I think participatory approaches are deeply important and can be and hold a lot of promise. I also think the way that they're understood often in machine learning and AI, maybe NLP research, is let's bring some people on board and assume that this thing will continue to be built and just have people tell us so we can avert some fairness related, or some other kind of harm, but we're going to build the thing. And not some people might tell us that we really should never build this thing and we should not build this thing. And so participation is kind of understood as let's open this up, but under the, under the assumption that things should continue, rather than let us dismantle kind of the power dynamics that have characterized technological development, which is kind of historically how participation is understood. So I'd be very interested in people's thoughts. I'm interested in thinking about participation as a way of opening up, but I have no idea how to do it kind of in the context of kind of large tech companies and maybe even universities in a way that is not extractive and not exploitative.
Also participation is might be specialized to particular applications, and general purpose development might still be attached. So I'm kind of
so fundamentally, I think the point is that participation, right, is political in nature, right? It's about dismantling kind of like power relations. And I worry, right, about bringing this into a field that understands itself, right, internally as apolitical.
So I kind of wonder about whether there are kind of safe, applications. And Eric talked about scientific discovery, and if you're training, foundation models, let's say on proteins, and which obviously still involve humans at the end of the day, but for the moment, or maybe you could do it on astronomy data. Is there cases where it's safe, and does that justify the use of those technologies there, or do we need some sort of more kind of blanket, slow down just because of the way things are kind of trending?
Just to support Sue's comments just now, I think it's always important to consider issues of fairness, equity, inclusiveness with any technology, because things pop out that you hadn't thought about before. For example, let's say with Copilot, which is in private preview right now, we have a team looking at safety and risk issues around that technology. One thing that's come up is, are people who are less educated, who haven't had the fortunate education that other developers have, more at risk of accepting code that they wouldn't put effort into understanding was broken or a security risk. And is that a new dimension of inequity when it comes to this kind of a service? And the same might be said, we can sort of dig around and we have to just be aware to think through implications of, even in biology, what that might mean, not even to the frank risks that people think about with biowarfare and malevolent uses of these technologies, but even just for the issues of who gets to use them, who gets to benefit from them. Industry, is it academia, are certain segments excluded, for example? I don't know if people would agree with me or not on this kind of just being sensitive.
Maybe I could ask a very kind of specific question, just to, we talked a lot about kind of general principles. So should GPT-3 be released? So we're talking, I want to get back to kind of this openness and accessibility. So maybe they're dangerous, but on the other hand, the more people to have them, access to these things, maybe the more we can kind of try to work with them and understand their behavior. So
I should this briefly.
Yeah, Jack.
Because I was at OpenAI when we decided not to release GPT-2, which was a controversial, fun decision that we made that led to a lot of debate in the community. But we ended up releasing it, and I actually think, in hindsight, I was really glad that we did. We maybe even should have considered releasing it slightly earlier, because it prepared our intuitions for GPT-3, which had like really weird scaled up properties relative to what was in GPT-2. And maybe to just echo a point Jacob made, like in the future, there are these long concerns about misalignment and the complex safety attributes of these models and scaled up ones. And if those models get built by someone, it might be better to have a really broad set of intuitions today about how to deal with it. So I think I net out weakly on the side of releasing, on the assumption that it's necessary to help us understand the future and how to orient ourselves towards it.
And the synthetic bio people have made this argument for many decades, several decades, I say many, but several decades since about 2000, that, hey, we should work freely because better that we understand this stuff so we can be there and ready to deal with the biowarfare that's developed by malevolent users.
It's not clear that argument has actually panned out that well, though.
Yeah, it's...
I'm just saying that's the argument.
I see, yes.
So I'm curious kind of what should be the community norm here when Microsoft or Facebook or Google or Anthropic creates the next large language model or foundation model. Can we just, are there accepted principles on how we should release and when and to whom?
Well, I think we have to move with caution. As you know, Percy, Microsoft, we had a general feeling of democratizing technology. We wanted to release our large-scale Turing models, representation models, as well as the inferential models to the public. And we had our analysis led us back, maybe echoes what Jack went through at GPT discussion days, early GPT days. We decided, let's go to private preview and work with academics and have invitations to have teams help us get eyes on this right now and explore these end directions and challenges, including their own questions. And that Turing academic program has led to interesting insights and learnings for Microsoft and for the academics involved. And that's going to expand over time. So it's kind of like stage one, it's early days, let's learn more, let's engage, let's license the technology out to academic groups in a competitive proposal process. It's still small compared to where we need to go. But I think one standard of practice we'd like to see evolve is there are approaches to phasing technologies by learning to understand them more, potentially working with partners and hopefully multi-party stakeholders to understand the risks and the benefits better.
I guess it's...
Percy?
Oh, sorry. Go on, Joel.
Oh, Joel.
Thanks. No, I think one way to think about it is even when working with these models that we know can have, of course, problematic behaviors, and that we may be worried about some people taking it on and using it for bad effect. it's the mindset of conducting the work towards the ability to release it openly. And so in a sense, if from the beginning you say, I want to conduct this work in a way that when we are ready to, to talk about it, to share it, that we are in a position to share the code, to share a full characterization of the behavior of the model. I think that's really important to have, to not start early from saying, oh, we may not be able to release this model. And, really from onset and all the way through the process of the work, to have this commitment to transparency and openness, I think is a really powerful way to do it. And, I do agree that it's an overall positive thing for the field to have GPT-3 released. I'm not saying that will always be the case for every model out there, but I do think it's a net positive. And I do think in terms of how we go about the development of such work, even in industry, it's really very, very important. I think we have to be careful about drawing a line between models and between data. And there's some cases where we'll never be able to release the parameters of a trained model because it draws on data that has some privacy concerns. We see this in the healthcare field. We see it including on some of the platforms that deal with user data. And so we have to figure out how to navigate that line. But the code itself to rebuild the models and so on, I think most definitely.
Yeah, I like the mindset kind of angle, especially since I think it's also a matter of time, because in 5 years, GPT-3 really being out there is not going to be probably a huge deal. Jacob, did you have another comment?
Oh yeah, I was just going to say, I mean, it seems important to me to have widespread access to at least auditability. I don't think just the more eyes, the better, right? And I think if there's ways to, maybe what the concern would be misuse, but if there's ways to audit without, providing kind of deployment access, then that seems very good. And I guess overall, I feel like if it's out there anyways, then you want good ways of auditing it.
Mm-hmm.
Yeah. I want to come back to Joel's kind of regulatory body idea, because it seems like there's all these discussions, and we only have 7 minutes left. And it seems like these are things that some body, some consortium should really be talking through and, looking at it from all angles. So what can we say more about what that might have look like, and who would be involved? What would the governance structure be? And, both, all different sectors, maybe even kind of internationally, how that would all kind of work out. So Joel, do you have any comments, or Jack?
I can open up to others. Go for it, Jack.
Well, I think that there is a policy need right now to understand biases in machine learning models. There are going to be other policy needs in the future, but that's the one right now which has attention and awareness. And it creates an opportunity because different bodies like NIST in the US and other ones in other countries are going to develop ways to evaluate for aspects of fairness. And that presents an opportunity for them to try and globally coordinate. So I think as a consequence of working on some of these urgent needs, we're going to build regulatory capacity to ultimately create scaled up kind of auditing bodies. And the drive towards needing standards gives us an opportunity for international coordination, which may actually help us have a well-resourced enough body in the aggregate that it can effectively look at the complex things being fielded by very large companies.
Yeah, I think international coordination is really here, because this is going to really intersect with geopolitical concerns. If the U.S. is trying to be really cautious, but China's pushing ahead really aggressively, especially if they plan to use it in military capacity, it's going to be a non-starter to have careful regulatory discussions in the U.S. So I think there needs to be some sort of international coordination, and that's kind of one of the things that's at least most troubling to me on the regulation front, how to actually get that.
Yeah, I see international regulatory activity starting with like-minded nations, but extending to nations that might have a different view on critical issues like human rights, as looking at really interesting challenges that are important in our time, such as how do we regulate surveillance technologies, AI being used for surveillance in a number of ways, and coming up with just uses that are just off the table for new international human rights conventions. AI technologies can freeze public expression. They can chill public gatherings. These have international human rights law per intention to date really reads on these things, and we need to go back and say, hey, wait, these are some technologies that will threaten them at the foundations. Let's get some agreements going there. Same for AI in warfare. I think in the commission that I just served on said, look, it's hard to come up with treaties right now per issues of definitions and notions of how technologies are used, for what's changed over several decades with AI technologies, today's technologies. But let's keep an eye on this, get some task forces looking at this very carefully and look for opportunities for international agreements.
Sure.
I'll just maybe inject a little bit of a maybe more cautionary view into this. I mean, I think I'm definitely aligned with what has been shared in terms of, aiming for alignment at the international level whenever possible. I think we also have to be realistic that given the rich space of applications of AI, achieving that on the international level is going to be very, very challenging. If we only see what's been happening on climate change and so on, the ability to reach that alignment is incredibly complex. And so we may also have to move faster on a more local basis and really commit to stronger points of views in terms of policy. I will also say it may surprise some people, maybe not those who've been around for a while, but even from the industry point of view, having clarity on what are these expectations, what should be, the burden of responsibility carried is actually something that's quite desirable in terms of driving how we do the development of that. And at this point, specifically for AI, it's so open and so unpredictable that does make it a lot harder to, even when you want to engage in a responsible way, to do so without having some alignment. And so I think it's a very much a welcome discussion. We should carry it out on the international level, but we can't wait for everything to be resolved on such a large scale.
Yeah, this is a really difficult matter. I'm just looking at the clock. Maybe this is a good time to wrap up. I just wanted to thank all the panelists again. That was a great discussion. We covered a lot of ground on the harms and opportunities, regulation, and I think this is something that's really important, I think, to all of us. So let's continue the conversation even after this workshop. So thank you again.
Thanks, Gracie.
Thanks, everybody.
Thank you. Thanks, everyone.
Thanks very much.
Everybody.
So at this point, we're going to take a brief 15-minute break, and then we're going to come back to session 2, where we'll examine the technological foundations of these models. So see you in 15. All right, welcome back, everyone. Hope you had a good lunch. Our next session is going to explore some of the technical principles that underpin foundation models. And the first session, we talked a lot about foundation models in context of language, but I want to emphasize that the general idea of foundation models go well beyond language. And today, in this session, we'll hear some perspectives from people from vision, robotics, and theory. So we want to begin with our first keynote speaker, is Yejin Choi. Yejin is the Brett Helsel Professor at the School of Computer Science and Engineering at University of Washington. She's also a senior research manager of the Allen Institute for AI. Her research interests include common sense reasoning, language grounding with vision, neural language generation. Her groups have built foundation models showing that they can be helpful in fake news detection, and more recently have been looking at how these models can be trained in a multimodal way. So Yejin, please share your screen and get started. Thank you.
Okay, so thanks much, Percy and Rishi and the rest of the organizers for the very timely and important workshop. I'm very excited to share my thoughts on the art of leaderboarding. Because these days things are really entering this era of extreme scale neural models, I seem to get extreme questions, such as, are you sure we can't reach AGI by just scaling things up? GPT-3 is so magical. Is it even possible to do impactful research from academia without extreme scale compute? And I seem to have to answer these questions periodically these days. And given that many modern AI leaderboards became practically the battle of size of models and data and compute, it seems only appropriate to draw inspirations from such books as David and Goliath, The Underdogs, Misfits, and the Art of Battling Giants, or The Art of War, where the key takeaway messages boil down to know your enemy, choose your battles, and innovate your weapons. Of course, we need to interpret that for AI research, which I would interpret as evaluation with realism and scrutiny. And thinking of new, diverse, harder tasks and leaderboard design. And then finally, innovating our tools through smarter algorithms and more complex data. There's actually a lot to unpack here. And in this talk, I'm going to highlight 4 different flavors of potential research directions that might be fruitful, which includes interactions, multimodality, knowledge, and algorithms, all with this recurring theme of getting smaller models working better than potentially larger counterparts. So let's dive right in. The first part is going to be about language grounding through neurosymbolic interaction in a 3D world, which aims to address this old question of symbolic grounding problem. And so there's this award-winning paper that introduced octopus test, whether octopus listening in human communications in language can really figure things out, the world outside the ocean that they're living in. And so in order to answer that question, we could try placing an AI agent in a simulation environment. In this case, this is a Thor environment where the AI might try to make some cup of coffee and drop the mug and see what happens. Probably it will break and make a lot of mess in the kitchen. And so in order to do that, what we need to do is somehow changing our neural architecture to allow for learning from the physical interactions and learning the causal common sense knowledge in a physical environment. And at the same time, we also want to learn language, especially how to communicate the knowledge that it learned about the world, the physical world. So in order to do that, the quick idea behind our model is that at time t, we have access to the environment, such as maybe there was an egg at a room temperature. It's not yet cooked and it's broken. And at time t+1, maybe the egg becomes now cooked, temperature is hot, and so forth. So we merge this sort of a physical dynamics into the typical transformer architecture for learning language. I'm not going to go into the details here other than saying that the bottom half of the page corresponds to typical language model without the physical interactions, whereas the top part is about learning the action dynamics, the causal effects of any actions taken onto different objects in the environment. And so the result, quick highlight, is that, well, our model can do much better than T5, which is 100 times larger than the particular tiny model that we chose on purpose, just for the sake of argument that for reasoning about physical dynamics in the world, in the even simple world as Thor 3D environment, the larger models cannot always do well, even if provided with a lot of supervision data. And here's an example, qualitative example, what we're testing here. So for example, at time t, there was mug filled with water, and there was also sink also filled with water. And the robot comes in, empties the mug into the sink, in which case the sink is still filled with water, whereas mug is now empty, doesn't have liquid anymore. Super easy for humans to reason, easy for Piglet, our model as well, though T5 tends to go with the language bias. And if mug is empty, maybe sink is also empty. So it doesn't really learn the common sense understanding of how the world works, even if we provide with a lot of supervision data encoded as textual sequence to sequence format. So to summarize this part, one way to choose our battle is to test large scale models for causal common sense knowledge. Even simple common sense knowledge might be too hard for large scale neural language models that didn't have any access to the physical dynamics. And we demonstrated that we can perform better with much smaller data. But the problem with Thor or 3D environment in general is that whatever the engineer encoded is all that we have. So for example, if we want to learn richer common sense knowledge, script knowledge about the restaurants, which one of the examples introduced in our earlier work, visual common sense reasoning. Well, Thor environment doesn't support this. A lot of existing 3D environment doesn't support this. In order to learn when a customer is pointing to another customer when the server shows up, we know from our experience that this means that person being pointed to ordered a particular plate, but there's no way AI agent can figure this out just by interacting in an existing physical world in the 3D environment. So this is really script knowledge about broader knowledge about the events, event participants, why people do what they do, what sort of events happen in what sequence. And so it really goes back to this beginning of AI research that try to write down some rules and roles, event participants and preconditions and post-conditions. But turns out, although we know all this knowledge, it's not that easy to write this out at scale. So it didn't go too far, except that now that we have a lot of data, especially lots of YouTube videos that are perhaps underexplored, the question is, can we learn multimodal neural script knowledge at scale? In particular, at the time of submission, we had 6 million YouTube videos collected. If you were to watch this, not sleeping, not eating, you need multiple decades to finish them all as a person. So what can AI learn from watching lots of YouTube videos? Well, in addition to the fact that there are some correspondences between object names mentioned through language and some objects that you see in the video screenshots, it's also going to be able to learn bigger events that define what happens or what happens in the kitchen. So we work with video automatically transcribe the text. And so this person is explaining what he's doing. And as you can see, the space of language is much, much richer. And there's a lot of information beyond the literal content of images. And then there's this notion of time, which adds to the causal knowledge, because without time, there's no causality. There has to be always between causes and effects some time gap. So using this rich knowledge, we can then write a new learning objective that can incorporate unique strength of this data that goes beyond the still images or just raw text. We can, for example, think about unshuffling frames in order to learn higher order event knowledge. And so we were able to do this. And the quick takeaway summary of this approach is that we can learn a fair amount of temporal common sense knowledge to the point that we can sometimes do quite well, even on zero-shot cases. And we achieve new SOTA on 13 different benchmarks that require some sort of visual, textual, and causal reasoning. And in some cases, we're winning over larger industry scale models. So also being in academia, we had only base size models successfully trained so far, but in some benchmarks, we are winning over a larger size model. And this power comes really from the complexity of information that's unique in YouTube videos. So next, let's think about another type of learning signal that I will refer to as knowledge, especially symbolic knowledge. In particular, I'm going to also talk about symbolic knowledge distillation, which will distill off-the-shelf neural language models to causal common sense models. So when people talk about knowledge distillation, we typically think about compressing larger language models to smaller language models. They're both supposed to do the same job. Whereas here we are changing the purpose of the larger model to do specialized operation, focusing on causal common sense reasoning. And in order to get there, though, I think I need to briefly share the context of this work. So my collaborators and I have been excited about this idea that language models are not knowledge models right away. We have to do something about the neural language models or neural models in general so that they become knowledge models. And so we studied symbolic common sense knowledge graph known as Atomic, as well as a neural common sense model or common sense transformers known as COMET. And both COMET and Atomic have a 2020 version that's ever bigger and better than before. And here I'm going to highlight, just in case you haven't seen what Atomic looks like, it's a lot of if-then knowledge. So for example, if someone gets their car repaired, then we can infer that probably as a result, that person needs to pay the bill, might need to call Uber for a ride. Probably this person needs a mechanic and money beforehand. So we can reason about preconditions and post conditions, especially involving people's motivations and intents and emotions. And then we can also reason about physical entities, such as, what can you do with money? You could potentially pay for repairs, but also you could fold that into origami if you want it. And then we can also reason about counterfactual or event-to-event relations, including hindered by relation, which is basically a counterfactual context in which an event cannot occur. So the car costs too much, then it's difficult to get it repaired, or I think it meant to repair cost too much, or the car is totaled completely. And so in our previous Atomic versions, everything was crowdsourced because back then, which is very 2020, last year, it seemed that machines cannot do this reliably. And in fact, we trusted humans better. So we had 1.3 million such if-then common sense rules written down over 23 different relation types. And just in case some might wonder, how well does GPT-3 compares to COMET? To give you a bit of a sense of a perspective here, our COMET is more than 400 times smaller than GPT-3, which is not available to everyone. With that in mind, GPT-3 is much better than GPT-2. The jump in performance is really admirable. But since it's too large, not accessible to everyone, if you want to use something smaller and better, then COMET can do better. So this is higher the better, I should have mentioned. It's accuracy judged by humans for machine-generated common sense inferences. And so previously, this power of a COMET came from human annotated knowledge graph. Now the question is, can we bypass human annotation altogether, or more or less, I should say. So here comes this idea of a symbolic knowledge distillation. GPT-3 is too large. Can we somehow compress it down to something smaller? And oftentimes when we talk about knowledge distillation, we tend to face performance loss. But here we happen to have something even better. So first of all, we generated atomic 10x. Now it's 10 times bigger, at least with respect to a subset of atomic 2020 relations. And it's much better, much bigger, and it costed much less. And in fact, it's also more diverse, it turns out, than human-authored atomic. So atomic 10x seems very promising, but the question is, are they high quality? Because in our previous evaluation of GPT-3's capability of common sense, it was less than 80%. It was something like 73. Depending on how you measure it, it's a 70 something. So that's not good enough compared to human-authored common sense knowledge bases, which have 86.8% human agreement with other humans. By the way, common sense knowledge is always a little bit elusive, and there can be some disagreements among humans. And so it turns out, although we can find a lot more correct knowledge generated by GPT-3, the overall quality is not as good. But it turns out we can teach Roberta to tell apart or filter out potentially worse knowledge. And if we do so, then we can attain quality that we've never seen before, at least not when working with the crowd workers. Depending on how much we are willing to filter, we can reach quality accuracy as high as 96.5%. And this is still much larger than ever before compared to atomic 2020. Atomic 10x is much bigger. The green corresponds to the size. It turns out this better atomic also teaches better COMET. And so the blue bar shows the system performance, COMET performance on common sense inference on previously unseen events. And it can generalize much better than ever before, and certainly it's much better than GPT-3, at least on this task. So to summarize, with GPT-3, now we have new potential for distilling it down to smaller common sense models by using that for generating the knowledge graph on its own. And so for the first time, we have a machine-authored common sense knowledge graph that's better than human-authored one in all criteria: scale, accuracy, and diversity. Now, let me briefly highlight entirely different line of research that focus on inference time algorithms, because it turns out, depending on different reasoning tasks or leaderboards that we're targeting, algorithms alone can make better lemonades out of off-the-shelf neural models. So here, the work is about neurologic decoding. And a lot of the times, we resort to sequence models for anything that generates language as an output: machine translation and dialogue response generation and image captioning. But there are cases, new fun benchmarks, such as CommonGen, where that recipe doesn't work very well. So the task is given a set of words. We have to use all the words and generate some sentence that's reasonable. Now, even with a very large amount of training data for fine-tuning supervised training, sequence-to-sequence models do not understand the logical constraints here, which is to use all the words given in the input. It learns to use some words in the input, but not necessarily all words. As a human, you do not need even a single example for this to fine-tune yourself on, because we just understand the logical constraints in a declarative manner, and we can operate with this right away. We have a similar issue with machine translation today, where some of the inflection rules, grammar rules can be violated, especially when the translation go against particular bias in language, such as gender bias. So to summarize, we have a lot of language generation problems in which at the decoding time, we need to deal with some sorts of logical constraints. In our work, we explored this through CNF form, conjunctive normal form. And this is basically a complex or convoluted search business, discrete search that I will just pass over. But the results were quite surprising to us, even for us. We had a hunch that this could work, but not this well. So here, the summary is that when you look at the coverage chart, so here the higher is the better, neurologic, whether supervised or zero shot or unsupervised, which are green and yellow, the constraint satisfaction coverage or ratio is near 100% all the time, regardless. The supervised approach using conventional beam search does better with larger models. So x-axis shows the size of the model, but it doesn't really fully learn the problem. And this is not, neurologic does not perform at the expense of the quality of language that it generates either, because Ruja Meteor in this task correlates well with the human judgments on the quality of the output. And here we see that unsupervised neurologic outperforms the supervised approaches. Not only that, unsupervised neurologic on smaller networks outperform supervised approaches on larger networks. So we found similar patterns across different tasks that our paper investigates empirically. So
1 minute.
To summarize, the premise of this talk is that scaling laws are real, denial is futile. Really, among my all-time favorite papers include this scaling laws for autoregressive generative model. The previous one was good as well, but this one really was turning point for me as well. And also, I can't imagine research without GPT-3 to T5 clip. Roberta, sorry if I missed your favorite as well. However, I don't think we can get to AGI just by scaling things up, because scaling laws explain only a necessary condition, not the sufficient condition as a whole. And so about these earlier questions that I mentioned, well, first of all, self-driving cars were coming for several years, and I don't know if it's coming in a decade even. And even when we look at what appears to be soft task, where AI achieves a human level or superhuman level performances, the same task with a slightly different input, even though those input should be easy from human perspective, the AI could make miserable mistakes that no human would make. And so essentially we're solving on your data set without solving the underlying task properly. And so about this earlier question, can we even do impactful research from academia? Oh yeah, totally. We just need to understand where the weaknesses are, and then think about the weaknesses really resulting from the current paradigm of deep learning, focusing too much on self-supervised learning on a lot of raw text, followed by supervision on a lot of exam problems. Now, this recipe is the winning recipe for a lot of leaderboards. However, not all leaderboards, in the sense that the moment the leaderboards test generative evaluation, where the model has to generate language output, there's a far gap between human and machine. And especially for tasks that requires logical constraints, we are very, very far. And the reason why it doesn't work is not necessarily because supervision itself is wrong. I think that there's something missing even from the foundation, which is self-supervised learning, in that as a human, we cannot really learn deep learning just by looking at a lot of Python code on our own. We really prefer taking a class or reading tutorials. And so humans learn much more effectively from declarative knowledge. And I think that's how AI might need to learn more efficiently as well. So to summarize, the art of leaderboarding, I think there's really a lot more strategies potentially possible than what are discussed in this talk. But really the limit is our own imagination and creative thinking. And the particular directions that I presented here aim to address diversifying learning signal, especially with emphasis on grounding, emphasis on the complexity of information, because I think that's really the gist of scaling laws. It's not just about the size, it's the complexity and diversity of the information that's inherent in the data. And emphasis on learning knowledge about the world, especially incorporating declarative knowledge, and then the importance of inference time algorithms. I think this is really underexplored, fruitful research direction that I'm excited to see more of. So I stop here and ready for questions.
All right, thank you, Yejin, for that wonderful talk. Really love the analogy there. So let's take some questions. One question is that it's really great that you're able to show these improvements with smaller models. There is an element of still trying to push up on scale. For example, Comet is 400 million parameters, which is not exactly small. So what do you think of the role of scale? Is there a kind of a minimum scale that you need to do kind of meaningful research?
Yeah, I think still the larger the better. So any of what I presented will work even better if someone puts even more compute, like especially inference time algorithms attached to larger models. Well, the gain might decrease. It may become more diminishing return, but always the larger is better in many cases. And I think that's because inherently, the larger models have seen more data. It's almost similar to how human researchers, we cannot get Nobel Prize just by reading a lot of papers, but it tends to correlate. If you read more papers, probably more ideas arise as well. So the diverse information is really important. I think the quantity of information, the complexity of information in the data is really critical. And ignoring all that, staying in a very tiny amount of data will not go very far, I believe.
Yeah, great. Another question from the audience. So data collection for these foundation models is a challenging issue. How do you collect the YouTube data given the express Google copyright not permitting downloads? This is a very specific question.
Yeah, so that we discussed quite heavily with lawyers on our end as well. And so the policy, I think, is probably debatable depending on where you're coming from, but we interpreted the fair use interpretation of it. Though because of this thresholding on download, it took a very, 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 very long time for us to collect the data, like really very long time. This project was going on and on for more than a year, maybe more like 2 years. And we almost gave up, but we didn't, because we're too curious to see what happens if we tried on videos.
Yeah, good thing you didn't give up. All right, that's all the time we have. Thank you again, Yejin, for the talk and answering the questions. So now we will move on to 3 10-minute talks. We'll start with Chelsea Finn. Chelsea is an assistant professor of computer science and electrical engineering at Stanford. Her lab is interested in how robots and other agents can acquire broadly intelligent behavior through learning and interaction. And more recently, she's been looking at how offline data could really help improve the sample efficiency online. So Chelsea, go ahead and share your screen and take it away.
Thank you for the introduction, Percy. So I'll be talking about the role of foundation models in robotics. Great. So in particular, I'd like to start by emphasizing that unlike other applications of machine learning, robotics is an area where we've seen a lot less success in real world scenarios. So in particular, this is a clip from, or several clips from the DARPA Robotics Challenge in 2019 that highlight some of the challenges that arise when you try to put robots into unknown environments. this challenge was ultimately considered a fairly clear failure because none of the robots were able to successfully complete all of the tasks. And I'd like to bring this up to specifically contrast it with a number of other areas of machine learning. For example, Google Translate, voice recognition, recommenders. We've seen pretty good functionality in the wild from these other machine learning technologies, unlike the kind of challenges we see in robotics. Also, in contrast, the DARPA Grand Challenge in 2005 was actually considered to be a big success in autonomous driving. And still today, we do not have autonomous cars in the real world. And so this just all goes to show that how challenging the robotics problem is. That said, it's not all failures. Robots can actually do some impressive things. So, for example, here's a video of a robot that learned how to use a spatula to lift an object into a bowl, which is a fairly dexterous task. That video was from 2016. Here's also a video of a robot performing parkour from Boston Dynamics in 2001. And that said, there's a bit of a catch. So in both of these examples, the behaviors that were shown in these videos were manually tuned for this environment, or specific to the environment that they're in. So in the case of the Boston Dynamics video, the parameters of the behavior were tuned for that particular course. And if you change something about the course, the robot would fall flat. And likewise for the video on the left, this was actually using machine learning. So it was actually able to adapt to this environment, but the entirety of the system was trained on 15 minutes of data from that particular environment. And so if you change the position of the object, if you change the spatula, the robot would also fail. And so essentially where we're at in robotics is that we can allow robots to perform complex maneuvers, but only in narrow controlled environments. And so in particular, there's this grand challenge in robotics of trying to allow robots to generalize to in the wild environments. And I think that we're at a really exciting place right now because we've seen foundation models pre-trained on broad data be a fairly successful and promising recipe in other areas of machine learning when we care about generalization to open world settings. That said, there is a bit of a catch, which is that unlike in other areas of machine learning, we don't have tons of data that's lying around on the web. We're typically operating in a setting where we have minutes of very narrow data that we collected on our robot because it's fairly time consuming to run experiments with robotics. And so the key challenge is we need to move from minutes of narrow data to days or weeks or even more of much broader data. Just like how it doesn't take humans just minutes to learn how to walk, for example. We need much more data and broader data at that. And so to this end, there's a number of interesting questions towards addressing this challenge of data scalability in robotics. And at Stanford, we're working on a number of different of these questions. For example, whether robots can collect high quality data with minimal supervision. So for example, this work used weak supervision outside of the loop of data collection in order to allow the robot to explore its environment. We're also looking at questions like how we can leverage data across institutions and across different robot platforms so that, like the rest of machine learning, we can actually share data across labs and reuse data more frequently. We're also looking at questions like how we can leverage the data from the web, which may not contain a lot of robots in it. And also, once we have broader data sets, whether robots can learn from this broad data with minimal supervision. And this involves algorithms like self-supervised reinforcement learning. Now, in the rest of this talk, I'd like to just zone in on one of these questions and get into some of the details. In particular, we wanted to study whether robots can learn reward functions using in the wild human videos. And this is a really important problem because reward functions are essentially a prerequisite for getting a robot to learn behaviors in the first place. If you don't know what the success criterion is, then good luck trying to actually learn the behavior. And we want to use it in the wild videos because it may allow these reward functions to generalize much more broadly. So what the setup looks like is we have lots of videos of humans in many environments with many tasks, and a narrow amount of robot data that was relatively easy to collect because it was only in one environment, only with a few tasks. We want to combine these two data sources to learn a reward function that ultimately doesn't just perform well in a narrow setting, but can also generalize to unseen environments and unseen tasks. And for example, we might want to give a human demo, a human video of a new task in a new environment, allow the robot to learn a reward function from this video, and then ultimately have the robot actually solve that task using that reward function that can generalize to new tasks and new environments. Okay, so how do we actually go about trying to address this problem setting? Well, many of the ideas that scale are the simple ideas. So the idea that we use here is also quite simple. Basically, we're just taking 2 videos and learning a classifier that can output whether or not those 2 videos are performing the same task. And you can train this using human data, using robot data, and using a mix of the 2. So for example, we'll pass in these 2 videos and train the model to output 1 because both these videos are closing a drawer. We'll also input these 2 videos and train it to output 0 because these are doing different tasks. And likewise, we can also give it pairs of human videos. And then once we have this classifier, we can use it as a reward function conditioned on a video of a human to tell the robot whether or not it's successfully completing the task. We refer to this as domain agnostic video discriminator, or DVD. And in simulation, importantly, we tested generalization not just to the training environment from which we had a narrow amount of data, but to new environments with new colors, a new camera viewpoint, and a new arrangement of objects. And we tested this on a variety of different tasks. And what we find is if we test generalization to new environments, if we only use narrow robot data, the performance isn't very good. But once we incorporate videos of humans into the data set, the performance improves by more than 20% when specifically looking at generalization to new environments. And in particular, this is an example of what that looks like, where we can pass in a video of a human, and the robot can use this to derive a reward function, which allows it to solve tasks not only in the original training environment, but also in a variety of other environments as well. Okay, and then we can also test generalization to new tasks as well. And again, here, similar to the environment generalization scenario, we also see a 20 to 30% improvement in performance when testing for this generalization. And finally, we tested this environment and task generalization on a real robot, where we trained on all of the diverse human videos that were in the something data set in combination with the narrow robot data set from this environment in these 2 training tasks. And when evaluating on new environments and new tasks, we see that we can essentially show the robot a video. It can use this to derive a reward function and then ultimately accomplish the task in this environment that the robot hasn't previously had. The reward function didn't see any data from this particular environment. Likewise, we can give it a video for another task, like pushing a tissue box to the left, and the robot can also figure out how to solve this task. And again, the reward function didn't see any robot data for either of these 2 tasks or in this environment. It leveraged the videos of humans from the web in order to generalize to these environments and these tasks. With that, I'd like to thank my students, especially Annie Chen and Suraj Nair, who led the work that I presented at the end. And happy to take questions during the Q&A period.
All right, thank you, Chelsea, for that interesting talk. Let's move on now to Tenyu Ma. So Tenyu is an assistant professor of computer science and statistics at Stanford. He investigates the theory of deep learning, reinforcement learning, robustness, non-convex optimization. And more recently, he's been looking at the theory of language models as well. So Tenyu, please go ahead and get started.
Okay, thanks, Percy. This is based on the section 4.10, the theory section of the report, whose lead author is Aditi Raghunathan, and also based on some recent papers with students of my group, Colin Wei, who is a rising 5th-year student doing some fantastic work on deep learning theory and theory for semi-supervised learning. So let me jump into the talk, which is on the possible theory of foundation models. So I guess let me start by talking about what we think would be the theory's role in studying foundation models. So ideally, as in many other engineering and science areas, we hope the theory could forecast outcomes of experiments and reduce the number of trials in the experimental process. In this context, it really means that you can save a lot of compute, which means you can save a lot of money and a lot of carbon emissions. And eventually, I hope the theory can guide technical decisions and inspire new methods. However, arguably, this list might be too ambitious for us for the theory in the current time. So the short-term goals are to formulate the problems, to analyze existing methods, and to explain observed phenomena. In some sense, in my opinion, these are necessary goals because if you don't understand existing methods, then you have to, it's kind of hard to inspire new methods. So these are what I'm going to talk about in the talk. So in my opinion, foundation models require some brand new theoretical techniques. And to demonstrate that, let's start by talking about what statistical learning theory, the standard one, can offer us. So in standard statistical learning theory, we train on some empirical loss, which is defined on some finite training data set. And then you evaluate on a population loss, which is defined on the population distribution or the infinite data setting. And the goal is to show that training on finite training data set suffices for us to test or perform well on population distribution. And the core is basically to show that these two loss functions are somewhat similar in some sense. And you can see that these two loss functions are indeed similar. It's the same task, the same loss function, the same model parameterization. The only difference is the p hat versus p. So basically, you have to show that the finite data set is a statistical approximation of the population distribution in some sense. However, for foundation models, the pipeline is much more complicated. So for example, in those methods with optimization-based adaptation methods like BERT, what you do is you train with the empirical pre-training loss, which is defined on some large unlabeled finite training data set. And the loss function, of course, also has to be unlabeled, for example, contrastive learning or multi-task language model loss. And then you adapt your parameters using an adaptation loss, which is defined on some downstream training data set, and also with some downstream labeled loss. And the parameters you adapted is also somewhat different from the pre-trained parameters. At least you need one linear head on top of it, and also you may train a subset of the pre-trained parameters. And then you evaluate on the population downstream distributions or the infinite data setting. So you can see that the challenges are that the theta and the gamma, the pre-trained parameter and adaptive parameters might be different. The pre-training distribution and the downstream distribution might be different. And also the loss function, the task between the pre-training and downstream setting are also different. One is unlabeled and the other is labeled. So our approach towards building a theoretical framework for analyzing this is to try to reduce to supervised learning as much as possible. So first of all, we see that between adaptation and evaluation, this can be kind of handled by standard supervised deep learning theory because the only difference is between D hat and D, and you mostly just have to show that D hat is an approximation of the population downstream distribution. And how do we bridge the gap between the other two boxes? So what I'm going to do is I'm going to introduce two more boxes to make the gap smaller and identify the most important issue in analyzing foundation model. So first of all, the pre-trained empirical loss probably should be similar to the population pre-trained loss because standard generalization theory. So you transfer from p hat to p. And second, on the right-hand side, standard statistical learning theory tells us that if the optimization can succeed, then you only have to show that there exists some gamma star, some parameter that can give you small adaptation loss on infinite data. You only have to show the existence to guarantee finally the algorithm can find such kind of like gamma star. So what we have abstracted away is the standard generalization between p and p hat and d hat. And also, we have kind of hide or assume the success of optimization so that we don't have to worry about it. And what we focus on is the population case, and which is what we call pre-training adaptation interface. And here, we only have to work on the population distribution, the infinite data setting, and we still have to deal with the distribution shift, the different tasks and loss functions, and the parameterizations between theta and gamma. So in some sense, this framework doesn't lose the essence of the problem and allows us to focus on the important aspect. And how do we establish this arrow? So far, we only have somewhat ad hoc techniques to show this based on the particular setting, the particular loss functions, and the particular data distribution, so on and so forth. I'm going to show two analyses, maybe in the interest of time, just one of them, for some concrete algorithms. And maybe in the future, we can modularize the proof further in the future. So I'm going to talk about contrastive learning briefly. So this is an algorithm that tries to learn representations by pushing representations of augmentations of the same image closer, and also pushing away optionally augmentations of the different images further away from each other. So in our language, this is a contrastive loss is the population, is the pre-training loss, and the adaptation loss is a classification loss with the adaptive parameter, which is the linear hat. And how do we bridge the gap between these two boxes? What we show is that if you have a small population pre-training loss, it means that your presentation has to have certain geometric structure. And the structure here is the distance between the representations has to capture certain kind of intrinsic distances between the examples, x and x prime. So what we're thinking is that we have like a manifold of examples, maybe a manifold of cat, a manifold of dog, and there are also submanifolds of breeds, different breeds, and the intrinsic distance is defined such that the distance between x and prime is close if x and x prime can be connected by a sequence of neighboring natural images. For example, suppose you have two French bulldogs here, which looks somewhat different, but we claim that they have small distance because they can be connected by a sequence of images that are neighboring images, and each of these images is a natural image of French bulldog. On the other hand, suppose you have a bulldog versus a Burman cat, then we claim that the distance is large because you cannot really connect the bulldog with a cat with a sequence of natural images. In this sequence, it must be some place where you have a kind of a half dog and half cat, which doesn't look very natural. I guess in the interest of time, I'm going to skip the second example, which is about language models plus prompt tuning. This is about the NLP setting, and we have to make different assumptions. And for example, we have to make a generative model assumptions on the data distribution, and we have to do some different approach. In the future, we hope that some of these analyses can be unified. And also, let me briefly mention that this framework is only is explicit or implicit used in many analysis. We only kind of like summarize this framework from the existing work. We didn't propose them ourselves, and it has been used in the past many times. Looking ahead, I think there are many technical challenges, especially for theoreticians. For example, we need to have proper and realistic assumptions on the population distribution. We need to have more mathematical tools to deal with these population distributions and characterize the internal workings of the models. As you see in a contrastive learning case, we have to characterize the what the representations, the geometric structure of the representations to build this link between the two boxes. And we also need toy cases for debugging tools and comparing bounds. And another open question is we don't really know how to have a framework for in-context learning. The framework we presented only works for those optimization-based adaptation method. For in-context learning, you have a different mechanisms, which seems to require different theoretical analysis. And finally, I guess the final goal would be to have some theory that can help with inspiring new methods in the future. We don't really achieve there yet, but I think it's possible in the near future. For example, in the contrastive learning paper, we did have a new contrastive loss, which is driven by the theory which have provable guarantees. And it turns out that the contrastive loss is comparable to the SOTA and doesn't require large batch training as well. So this is not something super impressive right now so far, but hopefully in one day we can have better theory that leads to better methods in the future. Thanks for listening.
Okay, thanks, Tenyu. Let us move on to the third and final talk of the session. So joining us is Tatsu Hashimoto. Tatsu is an assistant professor of computer science at Stanford. His research uses tools from statistics to make machine learning more robust and reliable. And he also works on language model generation and evaluation. Tatsu, the floor is yours.
Okay, great. Welcome everybody. I'm Tatsu Hashimoto, and I'll be speaking about some recent work by myself and my student Tianyi Zhang on understanding the inductive bias of language modeling and why language models learn to capture interesting structures such as syntax. Large language models and foundation models more generally have had an enormous and almost unavoidable influence. They have been behind some of the biggest gains in benchmark performance in NLP, and their use is ubiquitous in a range of downstream tasks. Shown here is performance on the SQuAD 2.0 question answering benchmark. And the marked red gap is the large jump in performance attributable to the use of BERT. There's a clear inflection point in performance when these models began to be used. More intriguingly, careful investigation into these models have revealed that they seem to learn useful linguistic structures, such as dependency parse structures, without explicit supervision about syntax. Shown here in the top is undirected arcs from dependency parses in black, and colored lines indicating arcs estimated by a linear classifier or a probe trained on the internal representation of BERT, a language model. It's surprising that simple and task agnostic supervision in language modeling leads to these kinds of emergent and useful structures. Recent investigations have further shown that it is easy for these models to learn syntactic structures compared to others. The example shown here suggests that we can learn with near perfect accuracy syntactic probing tasks with only tens of thousands of examples, shown here on the left, but these same representations seem to fail on reasoning tasks regardless of the number of samples on the right. And this is consistent with some of the things that Yejin was talking about earlier in this session today. This is a bit of a mystery. Task-agnostic self-supervision seems to encourage language models to naturally learn some types of structures, but not others. What do we know about this sort of interesting mystery? On one hand, there's a large literature in NLP on probing tasks that try to understand what types of structures are embedded inside the representation of these large language models. And we have a decent understanding of the information that is contained in these representations and the complexity of the probes that is required to extract them. On the other hand, recent advances in theoretical understanding of language modeling have characterized the conditions in which pre-training can provably recover certain latent structures. And this was covered a little bit by Tengyu's talk, such as recovering latent variables in fill-in-the-blank tasks, or recovering hidden Markov models via language modeling. There is, however, a gap in our understanding when trying to explain the observed empirical phenomena from before using these theories. We know what structures are learned by language models, and we know what types of toy models language models can capture, but we do not yet understand why language models seem to naturally learn certain structures, such as syntactic parse trees, from what is essentially task-agnostic supervision. As a starting point, we can think a bit about what is sort of a common framework in theory characterization for these models, which I'll call the closed hypothesis. In this hypothesis, language models acquire representations that are useful for downstream tasks because language models are trained to fill in the blank, and filling in the blank can sometimes directly provide supervision for downstream tasks. So let me give an example. In sentiment classification, we might have a case where the model has to fill in, I mask this movie. Clearly, our ability to fill in the mask is closely related to our ability to understand the sentiment of the rest of the review. Because of the direct link between the downstream task and the language modeling problem, this is fairly straightforward to analyze, and there is now well-established theory for studying these types of situations. However, this doesn't necessarily explain the actual behavior of language model training, because the vast majority of masking problems have nothing to do with a specific downstream task. As an example, we might mask out the word the in the sentiment example, in which case we get no supervision for any downstream task. It is these more generic masks that are more likely providing the inductive bias in structures identified by probing studies. Is there a way for us to understand how much of the gains of language models come from task-specific masks, as suggested by this closed hypothesis, and how much of the gains that we see come from these random masks? We can answer this question with a simple and well-controlled experiment. If we restrict ourselves to tasks such as sentiment classification, we can come up with 3 different ways to train language models. On the left, we can train models purely on closed-like masks, where we identify sentiment words using a lexicon, mask those out, and ask the language model to fill them back in. On the right side, we can consider the other extreme, where we remove all these closed-like masks and only consider masking generic words. Finally, we can compare the performance of these two extremes to random masks that are used to train language models in practice. So what does performance actually look like? Since we don't actually have the computational ability to train these models from scratch, we can use a more computationally efficient way to run this experiment called continued pre-training. And we updated a basic BERT model on 3 types of masks across 3 different tasks. Vanilla indicates the performance without any of this continued pre-training. And we see that using closed-like masks in red gives huge gains. This is expected and goes along with the established theory. What happens with masks that are not closed-like? We actually find that even after removing closed-like masks, we see almost 50% of the gains due to pre-trained performance remain. This is really surprising because we explicitly removed task-specific supervision, but still got gains on downstream tasks. Even more surprisingly, we find that there's almost no difference in performance between randomly masking tokens and the no closed masks where we explicitly remove direct supervision about the task. What this suggests is that masked language modeling works not because of the closed reduction, but because there's useful signal beyond direct fill-in-the-blank supervision. So what's missing in our understanding of masked language modeling? So to try to understand this, we knew that we had to understand how generic masks worked. And we looked towards other algorithms which also rely upon fill-in-the-blank style prediction tasks and to understand these connections. One major class of algorithms that rely on fill-in-the-blank prediction problems is the classic graphical model structure estimation problem. For example, the CMIT algorithm for estimating conditional independences in a graphical model consists of repeated tests of whether pairs of variables can be reconstructed given the remaining ones. This is basically a masking task. And the connection here is pretty direct. BERT-type language modeling seeks to mask some tokens and fill it in as a way to learn representations that are useful for predicting relationships among tokens. CMIT-style graphical model structure estimation algorithms seek to mask variables and reconstruct it as a way to see whether there is strong dependence among the variables. This brings us back to the high-level point. Masked language modeling is naturally designed to learn statistical dependencies among token positions in a sentence. We've shown this formally in recent work, and I'll refer you to our paper for full details, but I want to describe the high-level connection. First, since a masked language model gives the probability distribution over masked tokens, a language model implicitly estimates a dependence between any 2 tokens. Here, we're going to write this down as this I hat object here. What we can show is that the model's estimate of dependence and the true dependence must be similar, as long as the masked language model achieves low loss. More precisely, if a language model has low log loss on the fill-in-the-blank task, which is the term on the right of this inequality, then this log loss upper bounds the approximation error between the language model's internal estimate of conditional mutual information and the true population conditional mutual information on the left of this inequality. Thus, common masking objectives serve as a surrogate upper bound to learning statistical dependence. This is all nice, but why do we care? Let's return to our opening question. Why do masked language models seem to learn syntactic structure so naturally? We might hypothesize that it is because these models are learning a different type of dependence among tokens, statistical dependence. And this is a testable hypothesis of the theory. If this is true, then we should be able to first recover statistical dependencies learned by large language models like BERT, and then we can use these dependencies to construct a parse tree, and then finally we can evaluate this whole procedure as an unsupervised dependency parser. It turns out that literally just using conditional mutual information that is estimated in BERT serves as a reasonably good unsupervised dependency parser, even outperforming the classic DMV algorithm from Klein and Manning. Even nicer is the observation that minor changes to the type of statistical dependence that we measure seems to decrease performance, and that the type of dependence being implicitly measured by BERT is actually the best out of those that are plausible to try. This is a somewhat surprising finding from the empirical perspective as well. It was widely considered that mutual information alone could not serve as a dependency parser, and this low performance PMI baseline shown here was considered and ruled out in the original Klein and Manning paper. It is a nice side effect that studying the theory of masked language modeling leads to an empirical observation that certain types of statistical dependence do relate closely to dependency parse trees. To wrap up, there's 3 key points to this talk. First, I want to pose an open problem and a call to action. We have very little understanding of the inductive bias of language models and why these models naturally learn some structures and not others. Second, we proposed one way to answer this via statistical dependence estimation, but of course, this is likely just the tip of the iceberg. Lastly, this hypothesis led to an interesting validation and finding that statistical dependences in masked language modeling directly encode syntax. It's also encouraging to see that there's been recent work, such as PMI masking from AI21, that demonstrates these mutual information-based approaches can lead to improvements in language model training as well. Thank you, and I'm happy to take any questions in the Q&A.
All right. Thanks, Tatsu. Now I will invite Tatsu, Tianyu, and Chelsea back on stage, and we can do some questions. So maybe I can start out with one question is, I think of theory as most useful when it's kind of making broad source predictions about things that you can't do experiments with, when what's possible or not. And we're in a situation, Chelsea mentioned how foundation models, we want to really use it for robotics, but we're not really sure what's possible. Is there anything that we can say? Is there a theory that can tell us how successful foundation models would be for robotics?
I guess, maybe not yet so far, or maybe not directly so far, but I guess as we progress, hopefully you can probably, for example, one thing that the theory could say is to predict how likely the adaptive models can generalize. So maybe that could help to decide how many training examples you need, how many samples or trials you need, so on and so forth. I guess Chelsea knows more robotics more. I don't know too much about robotics.
I mean, regarding robotics specifically, I do think that there is a reason to believe that it might require more data than typical supervised learning scenarios, because you have a sequential decision-making problem where your actions can affect the state of the world in a very tight feedback loop. And this means that there are so many different possible outcomes that your robot might find itself in, so many possible situations. And as a result, you may need more data to try to better cover that realm of possibilities. And so, I mean, I think that we don't have that much theory on even the supervised learning scenario, but I think that it's very likely possible that any sort of results in the supervised learning scenario might require even more data in the robotic scenario.
Right. Go ahead, Thomas.
But on the flip side, that's a promising sign, because it seems like foundation models, like from the robustness section of the white paper in some sense, like they have provided some of the most promising general purpose robustness interventions compared to like some of the other things that have been tried. So if the issue is changing environments, it does actually seem like this may be a very promising direction.
Yeah, it seems like a big challenge throughout is bridging the gap between the pre-training distribution and the kind of the task distribution. We've seen some theory about, Tianyu, it's kind of the centerpiece of theoretical analysis. Tatsu talked about how, the gap between the task and the mask language model. Is there, I guess, on the flip side, I guess we often think about robustness as kind of a problem in, let's say, in robotics, because we want, especially if with physical systems, for things to be robust and reliable. So maybe this is kind of continuing on Tatsu's point. Is this synergistic? Is using foundation models make it, on one hand, we don't know how to think about the gap. On the other hand, we think that foundation models helps us bridge this gap.
I think part of the issue is it's very unclear what types of assumptions are appropriate. Like if you look at the landscape of theory papers, there's sort of these latent variable based methods. There's also some of the contrastive learning, like latent model recovery style methods for like topic models. And it's not clear at all what problem structures real world data follows. And so we can come up with great explanations for why things work and how we're bridging these gaps. But like, I think Tianyu's point, I think is good, is it's not clear which of those factors that we're modeling is actually impactful for any of these tasks. And I think that's a huge challenge that I don't know if there's even a roadmap to solve.
Maybe I can ask more specifically. So this idea of contrastive learning kind of shows up, right, in Chelsea's setting where you're classifying two images of same task or not. And I guess that's one objective. And there's, on the other extreme, there's kind of autoregressive language modeling where you're just modeling everything. And BERT, maybe masked language modeling, is somewhere in between. Do we have any sort of insights, theoretical or empirical, about what are the strengths and weaknesses of each of these? Is it a matter of compute, or does it depend on the domain?
I guess I can say some kind of like internal guess I have about the differences between these two. So at least if you believe in analysis that we have about contrastive learning, you can see that it heavily depends on the notion of class in some sense, or subclasses. And also it really relies on how do you design the augmentation, the positive pairs. So in some sense, it only captures those things that are captured in the positive pairs. And if you're, for example, in language, I suspect that the masked language model is stronger than contrastive learning because you can capture other aspects that cannot be captured by the designed, handcrafted augmentations that you do in the language, if you are going to do contrastive learning for language modeling.
I think that it probably also depends on the downstream task. In the work that I presented, we only needed to, for reward functions, you don't need to understand everything about the world. You just need to understand whether the video is showing the desired task or not. And so you can potentially throw away a lot of information. Whereas if you actually move towards trying to control the environment and try to actually act and learn behavior, then you end up needing a lot more than that. And we've actually done some work on learning these sorts of autoregressive models, except of video, of generating video, rather than of text, which is the typical language modeling case. And one empirical challenge that we ran into is these models just simply underfitting. I think that we probably need much larger models when we move from text to images and try to apply these same kinds of models. And which is rather unfortunate for all the reasons why larger models in language are unfortunate, but it at the same time, it does suggest that the successes in language may also translate to that once we do actually figure out how to scale those models.
I also think I think we don't necessarily have a full understanding of especially the empirical performance trade-offs between the different masking objectives. Like if we look back at history, right? GPT-1 came in, it was autoregressive. And then people switched to BERT style like masking, or like went to Elmo and then BERT style masking, which was ever less autoregressive. But now with GPT-3, people are realizing that like prompt-based methods can now sort of like extract a lot more information out of these autoregressive models. I think the jury's still out on what the right contrastive loss or like self-supervision loss is until we sort of figure out also the right fine-tuning and like the right representation extraction strategies in addition to training.
I wanted to maybe ask about, prompting and kind of this close. So Tatsu's talked about how there's the representations that you get from kind of masked language modeling, and then there's the kind of more explicit close reductions where maybe the objective is the thing that you actually want to solve. And I wonder if that is kind of language specific, or whether there's analogs in vision, or is vision more about kind of just learning the right representations? Is language somehow special in that there's this kind of prompting and close behavior, or there's something more general here?
I think it's in the language case, the prompt can be the label itself, which I think is maybe unique. But in vision, there's also these sorts of infilling objectives, which are very, very similar to masking. And in fact, like Jason Lee's paper on analyzing these kinds of like fill in the blank style supervision, like does these kinds of vision experiments. And so I think the supervision itself is not unique at all, but whether there's something special about using the label as the target mask, I think is a different question.
I also don't think that it's necessarily specific to language. I think that you could imagine a scenario where a robot is acting in the world and collecting data. It does something, and then it sees that a human is unhappy, or it makes an unhappy face, or maybe the human says something. And if we actually have robots operating in those environments, then it's basically the same as the language case, where we just want to essentially get the outcome where the human is happy, or whatever we're optimizing for. And so it may not be all that different, although at the same time, we might be quite far away from robots operating environments in which humans are in and so forth.
Actually, one thing that could be interesting here is that, a lot of vision tasks are kind of associating a higher level semantic label with, an image. I guess there's segmentation of the 3D reconstruction. But in robotics, you could argue that the ultimate output is the control. which is now back in the kind of the space of, it's almost like you can just do language modeling in some sense. Now, of course, there's the problem that you don't observe the control signals sent to humans or robots, perhaps, and you only get weak supervision. But I wonder if that can be a powerful metaphor and analogy that helps us think about autoregressive language modeling just on things that happen in the world.
Yeah, and typically when we train these video prediction models, we do actually condition on the actions that the robot takes. And when we have robot data, typically we have both the observations as well as the controls that the robot took. And that is really, incorporating those controls into the system is really critical for actually learning the behavior, as you might imagine.
All right. Let's see if there's any other audience questions. Maybe we'll just wrap up now. So I would like to thank the presenters, Chelsea, Tatsu, and Tianyu once more. And that concludes the talk portion of the session. Thank you. All right, next, I would like to invite Chris Manning to moderate our next panel. Chris is the Thomas M. Siebel Professor in Machine Learning and Professor of Linguistics and Computer Science at Stanford. He also serves as Associate Director at HI. His influence on the field of NLP, I think, is pretty hard to beat with his famous textbook and his early work in driving deep learning and NLP. So welcome, Chris, and take it away.
Thank you, Percy. And in turn, then I'd be delighted to have the panelists join us for this second panel session on technological foundations. So if all the panelists would like to join and turn on their video now, that would be great. Okay, so I have 5 panelists to introduce. But, I thought maybe what I could do is introduce people in pairs and then have them answer a question as we go along. So, and this is going to be tricky because how can you introduce 5 people in pairs? So I thought I could clone Natalie and have her be in part of 2 pairs, but we'll get to that in a minute. So maybe the first pair of people I can introduce is, so first of all, there's Sanjeev Arora, who's the Charles C. Fitzmaurice Professor of Computer Science at Princeton University and has been a really prominent contributor to work on theoretical models of machine learning. And then there's Natalie Schluter, who's both a senior research scientist at Google Brain and an associate professor of computer science at the IT University of Copenhagen. So I thought I could maybe first start by asking the pair of you. I think it's fair to say that the dominant strategy we're seeing at the moment, perhaps especially in industry, is that if you build these models big enough, amazing capabilities will emerge. And so I was hoping to get your thoughts on whether that seems a workable strategy that will keep powering us for the next 5 years, or do you think that there are important theoretical questions that really need to be worked out to continue making progress? Like, how can we make use of theoretical and mathematical tools to give us a better understanding and drive further progress?
Maybe I'll take a stab first. Firstly, I want to say this has been a great event. I've been listening to the amazing talks and discussions all day. Fantastic. So I guess about this question, is big enough all we need? I'm guessing that we need more capabilities in the model. At this point, these models are a little bit reminiscent of the Vannevar Bush MEMX machine, storing all the world's knowledge. It seems feasible at this point that they could do it, but then to reason about it, that's the open question. So we probably need new ideas there, like probably some measure of knowledge other than cross-entropy loss for prediction, because the goal, after all, is to do this kind of reasoning later on. So some kind of test of reasoning, maybe. And probably better training algorithms and better architectures. I mean, those also probably need some more work. Over to you, Natalie.
So I think Maybe it's funny that you ask us too this question, because I think like for us too, it's kind of the opposite of maybe what the trend is in NLP right now, which is just build the systems and just see what happens. And it's kind of a really different way to approach, I think, like traditional computer science or mathematics, where it's more like in biology and medicine, where you kind of put stuff together, or in experimental physics, you put stuff together, you see what happens in the end, and you take some observations down. And I think the difference is that when you are doing this in biology or in medicine, and you're actually thinking about making stuff for humans or making stuff for living beings, that there is some sort of protocol that you have to follow to ensure that you're not harming them. So I don't think that you can just bash some stuff together, see that there's some good progress, and then release a medicine onto the world. You actually have to follow some very careful situations, very careful experimentation to make sure that you're not doing some harm. And I think that our field hasn't quite realized that there is this parallel. There's this switch in working, and there's this parallel that we have to recognize, and we have to observe like other parts of science do. But so I could talk about this for ages, but you might want to.
Okay, maybe pull out the first answer and go on. So let me introduce another two of our panelists. So Kavita Bala is the Dean of the N.S. Bowes College of Computing and Information Science at Cornell University, and Jitendra Malik is the Arthur J. Chick Professor of Electrical Engineering and Computer Science at the University of California, Berkeley. So both of you, I think, are primarily vision people, or at any rate, primarily interested in the physical world. And so maybe you could both start by sort of saying something about the importance of the physical world, vision, sensory grounding, sensory motor grounding, to pursuit of AI, and to what extent foundation models are lacking that, and whether it can be addressed. Do you want to go first, Kavita?
Sure. Jitendra, do you want to go, or I'm happy to go?
I can go as you wish. We can toss a coin.
Well, we maybe go back and forth a little bit. So this is a great question. So first, I have actually been enjoying also watching the workshop. So thank you for organizing this. I'll say I've struggled a lot with this question of where physics sits. And I'll say Jitendra sits on the vision learning boundary. I'm in the graphics and vision boundary. So I sit very much, and I come from the graphics tradition. And we in graphics have spent a lot of decades getting the physics right on things. And so and actually Percy said it this morning. He started off saying he was a skeptic, but then these new foundation models have made him question that, the time has come, a paradigm is changing. And I admit I also sit in that space, but I go back and forth, and I'll explain some of my quandary. So one is, I do think these foundation models are fascinating. There is a lot of opportunity for them to achieve many of the things that maybe in the past we would think that you would need a physics engine for, let's say. So, they can produce a lot of the generation aspect, producing the level of realism with DALL-E, et cetera, is just astounding, the kind of output that they can produce. So when I first started, I always used to think there's a place for physics. Then I see the kind of output that comes with this, and I think, wow, where is the place for physics? And I'll say there's still room for the place of physics in at least two places. Actually, three places maybe. First is you want to simulate, and so the physics engine is the one that produces all the data maybe that you can use. Your real world situations aren't going to give you enough data, so you can use it for simulation. But the bigger issue is every time in computer graphics, when we found that we tried to fake something, controlling the output is very, very hard. You can produce something very plausible that fools people a lot of the times. And then when you want to actually control it to get to a particular output, that's very hard to do. And that's where you actually, if you look at the movie industry, they actually go back to simulating the physics right from first principles rather than doing approximations, because it's so much easier and cleaner if you actually understand the physics. So that's another place where I think physics plays a role. And finally, in inverse graphics, when you're actually trying to understand what what goes into the world. We have these differentiable rendering engines now. There's room for them actually to help you understand what's going on in the world. And it's hard to fake that without having the real physics in there. So I think there's room for physics in all of these places, but I'll turn it over to Jitendra and get his input.
Yeah, so I think I'm going to take a more directly critical role. If not from the point of view that these models are not playing a very useful role in machine translation and speech recognition and a lot of sort of language tasks, and I grant them that. I want to take a very strongly critical role when we're talking about them as the foundation of AI. In fact, I think the term foundation is horribly wrong. These models are really castles in the air. They have no foundation whatsoever. What is the foundation of intelligence? We can take an evolutionary view. Okay, 500 million years ago, Cambrian era explosion, you have animals that can move and that can see. And it's the sensory motor loop which develops the basics of intelligence in insects and all the way through mammals and so forth. Okay, 5 million years ago, we can talk about manipulation, the hand, the importance of that. And then maybe in the last million years, we can talk about language. Or you can take the life of a single individual. We can take a baby from birth. What is the baby initially doing? It is seeing, it's putting things into its mouth, it's touching, it's doing multimodal interactions, it's doing experiments in the world. That's what Alison Gopnik calls the child, the scientist in the crib. And through those interactions, experiments, observations, it builds up a model of the physics of the world. What happens to objects when they fall? What happens when somebody shouts at another person? Social interactions, etc., etc. On top of that, at some stage, language comes in. So language is added on top of an individual who's very embodied, interacting with this sensory motor world. Now, at some point, the child goes to school and then reads books. And at that point, doesn't have to look up the meaning of words, can figure out meaning from the context of other words in a sentence, and then Wikipedia and so on and so forth. So there is a role for language. My colleague Alyosha Efros would say that we should stay away from language for the foreseeable future and developing language AI, but I'm not so extreme. There is a role for language. But this language is on top of this sensory motor entity. Like 90% of intelligence is there in a dog or a cat. That is what we need. So the language that we have right now in these models is not grounded. I mean, we know something from 30 years ago. There are these papers on this stuff. This is like going back to ELIZA or something like that. There is this fakeness here. There is no real understanding. And I think that this needs to be recognized and called out. I want to commend Yejin, because at least there is one person I can see in the language community who sees this, and I liked her talk very much because she was calling out the need for sensory.
Jitendra, maybe we should wrap up there for the intro. Yeah, there's clearly more to talk about on that topic. We need to build a foundation. It needs to be grounded in sensory motor. Yeah. Okay, thank you. But we'll get back to that. So finally, let me introduce the fifth panelist. So if you were around for the talk earlier, you saw Yejin talk. So Yejin Choi is the Brett Helsel Professor at the Paul G. Allen School of Computer Science and Engineering at the University of Washington, and also Senior Research Manager at the Allen Institute for AI. So for my third question, I will have a straight language question. And although both Natalie and Yejin do multiple different things, I will count you as the two language people. And so let me ask a question about language. So with the recent models like GPT-3, there's evolved this way of doing fine-tuning, if you want to call it that, or few-shot learning, where you're simply giving a prompt to a huge language model, that you're giving it some text and that then drives its behavior. I mean,
what do you think about that? I mean, you could think that this is just a horrible hack, or you could think, oh, this is brilliant because now we're moving to a world where we can control the behavior of these models by talking to them, just the same as we can get human beings to do different things by talking to them. Maybe Yejin first and Natalie.
I'm sort of itching to respond to Jitendra's
leave that till afterwards. We can do that next after the intros.
I focus on the more imminent question to answer. So I love it. The fact that we could probe GPT-3, what it knows and what it doesn't know through language. And I think this is really, really important going forward for the following reason. I think it really increases the expressiveness of our interfacing mechanisms with learned models, because the language is the thing that we do understand as human. We cannot understand anything else as well. Whenever we develop some new labeling schemes or new logical forms to describe some meaning to the machine, then we have to teach ourselves that symbolic mechanism, which almost always not as expressive as natural language. And I think going forward, maybe we could even do that more with vision models as well, in the sense that the way we understand what vision models know or not know, say CLIP model or DALL-E, language is really convenient there as well, because it allows us to explain or describe a lot of complex things beyond just categories of things, objects and actions.
Yeah, I mean, this raises a couple really interesting points. So one point follows from what Yejin was saying, which is, I mean, if these models are capable of, like, you know, solving problems that actually we as scientists haven't been able to decipher ourselves and give the instructions to a machine to do, then can we actually learn from the models themselves how to actually structure the different tasks? What do they consist of? How do you get this performance and without actually us knowing what to say to the machine to do? But on the other hand, I think it's really interesting that you can get these models to do a variety of different things, but then I am more interested in how these models are approximating a lot of different tasks at the same time without actually telling them precisely what to do. So, you know, picking apart these things and finding out what the mechanics are. Maybe these are two sides of the same coin.
Okay, thank you. And so now we'll move on to sort of the more general part of the panel. I think I'll turn immediately back to this issue of grounding, because that was raising a lot of passion. But in general, so for the panelists, feel free to jump in if you have something to say, but equally, if you want to, under the sort of reactions button down the bottom, there is a raise hand. So if you want to raise your hand to signal that you do want to get a chance to speak, I can also help make sure that you have one. And then for people who are watching this, we're happy to get questions from the online audience as well. So do feel free to enter them in the Slido interface that's available online, and we'll see what we can get to. But let me get back to foundation models and grounding. So, you know, I'll be quite frank. There's a rich history of how we came up with the name foundation models, but it has had bimodal response. Some people have said positive things about it, and some people have said very anti things about it. But, you know, one of the reasons why we chose the name was our feeling was that the same general kinds of techniques of using self-supervised style learning over extremely large amounts of data, which was pioneered in the language realm with models like GPT-3, would spread to other modalities, and people would be doing exactly the same thing with vision models, with models in robotics. And so we wanted to think of foundation models as not something that was language specific, but in general referred to using a huge amount of world knowledge that you were slurping up from the environment around you. Normally it's a model given data actually. And out of that, using self-supervised style learning techniques, you could learn a general foundational base of knowledge, which you could then apply to particular tasks. And so it wasn't meant to be all about language. And so, I agree, and I presume everyone on the panel would agree that grounding and the physical world is super important, even as me as the most singularly language person. So, I mean, if I perhaps start again with Kavita or Jitendra, do you think there are prospects for using the same kind of techniques of simple self-supervised learning tasks in other modalities and sensory fields, for touch and vision, to build the same kind of general purpose foundation that you'll then be able to use to better understand the world around?
Can I?
Sure.
No. Yes to self-supervision, but not in the way that language models work. Okay, let's start by building a dog. What do you need is, you need knowledge of physics. You need knowledge of how objects interact. You need knowledge of social physics, how agents interact. So what is very important is physical simulation. So yes, I believe in self-supervision, but the self-supervision comes from the fact that we live in a three-dimensional world with which we interact. And we interact with objects. A child pokes at something and that something falls. That is self-supervised learning. But this is a very different self-supervised learning than doing the closed task in natural language. But through a collection of those experiments and interactions, and observation. So some of it we do actively, some of it we observe. That is how we build the substrate for intelligence, and that's how insects do it, and that's how dogs do it, and that's how primates do it, and that's how humans do it. On top of it, language provides a communication ability, and it transcends various barriers because we can talk about things which are not there and so forth. There are these so-called 11 things which are special about language. And I don't want to detract from the role of language, but language without grounding, go back and read about Helen Keller. Helen Keller was, the process of how she was taught about the real world was very interesting, and how she learned to speak. It had to start with grounding. It doesn't have to be vision. I won't be a vision chauvinist. It could be audio, it could be touch, but some grounding through perception of the real world is central. Kavita, to you.
Well, not surprisingly, I kind of agree that you do have to have that interaction as the part that you build on. That's sort of our foundation that we build on. So that's the direction from which we come to it. And I do agree that that's sort of, but I do see a path for using that to build up to the kinds of models. They're rich and they can simulate. I mean, there is a generation part that is incredibly powerful in what these things have learned. But as I said, I think you get into this uncanny valley mode at some point. You actually need to get the rest of it to be able to understand what you've actually learned.
Oh, okay. Well, maybe next to Sanjeev to reward putting his hand up, and then after that, maybe hear from Yeji and her thoughts.
Yeah, I mean, I wasn't sure either what foundation referred to. At the first idea I had was this was some kind of an Asimov joke or something. But you know, I think I did interpret it fairly broadly, as you said, and you know, all the things that are in these models already allow them to, in principle, learn in the way that Jitendra is asking. You know, with attention, you can easily modify the input or the stimulus and see what happens, right? And try to predict what happens and see if that happens. So yeah, I guess I'm it does seem to have enough capabilities to do the kinds of things Jitendra is asking for, syntactically.
Okay. Gee, I said Yejin and then Natalie. Yejin.
All right. So I think I agree and disagree with Jitendra about the importance of interaction and grounding. In that, totally agree with you that both interaction and grounding are important, but language being grabbing more attention in the recent models such as CLIP and DALL-E, and insisting on following the evolutionary route, I don't think that's actually fair blame on language in the following sense. I think there are two problems. One is that both interaction and the grounding can be purely language as well. From especially NLP perspective, we consider even social grounding. There can be other kinds of grounding of the meaning of a language as well. And then speaking of which, interaction can also be purely linguistic or language-based as well. In fact, GPT-3 is in some sense interacting with us, but not in the ideal way, in that it's not asking us questions in natural language about what it doesn't know. But I would love to see a future research direction in which the AI agent can actually ask questions and seek information with more agency than how it's taught today, which is to give a stream of randomly ordered text. And as a human, we cannot learn that way either. We cannot just watch text and videos in the order of a sequence given to us without having the opportunity to ask questions. So I think interaction is missing there, grounding is missing there. Language may not be the key culprit there. There may be broader range of interaction and grounding that we are missing. Another aspect to this, in my mind, about the perceptual grounding is the challenge of robot and 3D simulation environments, because they tend to be fairly limiting. And I don't know, in my lifetime, I will see a robot or 3D environment that really matches the complexity of babies' experiences, let alone grown-ups. So we might be, in the meanwhile, looking for shortcuts for bootstrapping learning through language. And at the end of the day, I learned about tiger, for example, only by reading about tiger, not actually being eaten by a tiger or seeing somebody being eaten by a tiger. But I believe, I read about tiger in text, and I believe that they are scary beings. And I can even imagine visually how it might look if it were to attack somebody. Similarly, let's just say, okay, tiger may be an extreme example, even like chewing on an apple, that juicy, crunchy feel. I don't think we can build a robot or 3D environment in which the reward signal is actually equivalent to the experience that humans have. So this is just impossible dream to have, that AI agent can have the same experience as humans do. And so when faced with that, it seems that whether we do perceptual grounding or not, and how well we could do in it, it seems that we also have to figure out another route through which AI can cheat a lot of knowledge by digesting a broader range of data. And that's one thing AI can be very good at.
Okay, maybe I'd better go on at that point and give Natalie a chance to say some thoughts.
So I think so it is quite an important topic and a very popular topic that people are talking about, like with language grounding. I mean, there's other modes of communication that are completely ignored at text level as well. And I guess we also have to take into consideration that, well, babies actually can't read. So like what can you do as an adult by just reading? There's this interesting theory, linguistic theory, that posits that you can actually reduce the meaning of words to a very small group of primitive meanings. And that by combining this very tiny group of primitive meanings, primitive words, that you can cover all of the vocabulary of a language. And I'm wondering if, rather than this really broad question about grounding, because like, well, how much grounding? We're grounding here, grounding, what is the limit? What do you actually need? Is there a small amount, finite amount of interactions that are required to be covered in order to have like the foundation for language, or is it just infinite as well?
Okay. So a little procedural change. Actually, the production team would prefer that we don't use hand raising. So I guess we'll have to work on people jumping in with comments. But let me sort of continue a bit more on this issue of the sort of human learning. So, there's no doubt at all human learning is normal human learning. There's a complete range of sensors and grounding in this physical world. And even in cases where kids don't get the complete range of experience, there's still very much this grounded world. And so that's super important. And part of that Jitendra was starting to touch on was actually also interaction, that it seems that children only really learn successfully when they're actually learning themselves interactively, as the scientist in the crib, that you don't successfully learn by watching TV shows. And so both of those are clearly very important to how humans learn, and there's certainly things that we want to be sensitive to. But, on the other hand, it's kind of amazing how successful that this learning from a pile of data learning has actually been. So whether it's how much about language you can learn from something like a BERT or a GPT-3 model, or even like for some of the work that Yejin was showing, where you take a huge amount of YouTube videos, you can learn an enormous amount about the human world and how things operate. So, I mean, in some sense, because it's easy to do, that form of learning has been much more productive for advancing AI, I think, than people who've been trying to do grounded learning. So I guess the question I wonder is, can we ride this horse further? Can we, keep on working for another 3 or 4 years and leave worrying about grounding interaction for later? Jitendra. Sam.
Yeah, I want to say one good thing about this class of models, where I, having expressed my critique, would like to use them, is in multimodality. So vision does blend into into cognition, and vision does connect with language. And in the conceptual world, these transformer architectures are a very nice way to bring together different kinds of different representations, different kinds of information, knowledge, modalities, sound and text and images. So that's my one checkpoint in the favor of what you said. My negative will be, I actually feel that the world of sort of physical simulation and learning from video is actually making a lot of progress. I have devoted my energies to this in the last few years, and I think we are making great headway, and we are going to get good models for vision and robotics and connecting into cognition as well that way. Then I want to conclude with asking you a question, all you language types. Do you believe that these GPT-3 type models, how will they help you with chatbots? So the reason I'm saying I'm picking on chatbots is because I think dialogue is a central aspect of human language, right? It's not just lectures. We communicate, we talk. I ask Yejin a question, she replies back. We have this communication. After a while, both of us have a mental model of each other. There are these postulates of conversation and so forth, going back to Grice and so forth. Okay. do GPT-3, will you be able to build really intelligent conversation agents with GPT-3 type models? And if so, please show them to me. And I'm asking you in your world of language, whether you believe that will happen. I will take my answer off the air, as they say.
Well, I think I'm not meant to answer questions. So maybe one of the other three people who've worked on language would like to have a go at that one.
Just a clarifying question. So Jitendra, by these kinds of models, you are assuming like the masking is done at random points or something, like you're just predicting what's already there.
To be concrete, take something like GPT-3, and I want to convert that into a conversation agent so that we could have a dialogue for like half an hour on on some topic. And how would, as opposed to generating text following a prompt, for which these systems do a pretty impressive job.
I could answer at some point.
Go for it.
Though it seems I cannot type in the chat box that I want to respond. Chat is disabled. But anyways, so no, absolutely not. In fact, it's so fun pulling bad examples from GPT-3 DaVinci, if about chatbot. Indeed, it's harder on GPT-3 because people-to-people, like regular conversation, probably doesn't exist as a large amount in internet data, but also because it's lacking mental models, it's lacking theory of minds, and it's also lacking common sense understanding about social interactions and whatnot. So the fact that we root for language, though, doesn't mean that we are against knowledge models or theory of mind models. We can still work on all of these wonderful things through language as well. But I'm also into grounding. So I'm not against the grounding. It's just that there's limitation to how much we can ground depending on what sort of a grounding we are doing.
No, so great. I mean, thank you for saying this. So because that is part of language understanding, this ability to have mental models of other people, this ability to have explicit knowledge of the old style variety, scripts and knowledge graphs and so on. And I'm arguing that this obsession with GPT-3 means that you're ignoring some of those old ideas, which are, I think, very important.
Right. So the common sense transformers that I introduced earlier, people started using it for improving dialogue systems as well. Other people beyond our group started using it in order to improve the sig-to-sig models that cannot really say sensible things. Adding common sense model on top doesn't necessarily make all the conversation perfect yet, because this is something that came out only 2 years ago, and 2 years is too short to solve a major challenge. But I think it may be a potentially fruitful research direction to pursue further.
So actually,
I wanted to make one other.
I think Kavita wanted to go first.
Sorry?
I think Kavita wanted to go first.
Actually, I wanted to follow up on that. Actually, as a non-language person, it would be great when we're talking about these models to actually understand what the realm of application we think really is, because we don't think it's everything, and certainly not in the current state, right? They don't explain what they're doing. There's no understanding of why they produce a certain output. It's pretty random, and people know that they can play around with it and get pretty crazy outputs. So it'll be good to actually, and I think you Chris, you started saying, are there theoretical properties, but theoretical properties even feels sort of more, we're pretty far from that. We're talking about very broad brush, maybe properties of what it can and cannot do at a very high level, that you can prune out a whole bunch of areas that we just don't think it's going to address, not in the current form in which it's approaching it, versus those where it is, right? Unless you add a little more thought in, more understanding into it, it's just not going to get there. So it'll be good to have people comment on that aspect too.
Yeah. You going, Sanjeev?
So I think one thing that may clarify a little bit is, that the way, humans have the famous paucity of stimulus, right? Especially for language and many things. So their mode of learning may be different. And we know classically in even simple settings, query-based learning can be more efficient, exponentially more efficient than just distributional learning. So I think the interesting thing from a theory viewpoint is just that you can do so much learning GPT-3 style from just passive examination of data. So yeah, this doesn't mean that maybe the query mode isn't important, but what is surprising is that you can get so far.
So maybe I should move on and ask about a question that someone in the audience was asking about improving our technological foundation. So we seem to be in this world where this idea of having prediction of mass stuff, most commonly a word, with the transformer-based model is sort of the new normal, right? That it's everywhere in language, and it seems to be increasingly spreading through vision as well. So the question is, well, what should we be thinking about for improving our architectures for the future? How is that architecture not capturing the kind of ideas like grounding that people are arguing is so important? Any thoughts? This is a hard one.
So I think there are a couple things that we have to be really careful about, and this is kind of related to some comments that I had before. One thing is security and privacy, really making sure that these models aren't not only copying and remembering information that they shouldn't do just from like a security point of view, but also like an ethical one. Since they're not able to determine whether what they're learning, the information that they're learning from is actually ethical information, or not racist, not misogynist, etc. These are also big spaces that we need to still work on today, like ethical computations that we do really easily every day as humans. Just even being sounding human, like sounding cohesive from 3 sentences ago to 2 sentences later. This is a problem as well.
Right. I guess the question is there things that we should be doing kind of architecturally to improve that? I mean, like if I sort of push back slightly on the cohesiveness one, it seems like if you compare GPT-2 and GPT-3, GPT-3 is way more cohesive. Like it will seem cohesive for multiple sentences at a time. So do we need an architectural change, or do we just need to pour in more data and stir?
Or more memory?
I would vote for architecture change. Data change as well as architecture change. But what I mean by data change is that not just the raw data. Right now, we rely just on raw data, but we could rely on raw data plus knowledge graphs, plus maybe other means of QA interactions. As far as architecture goes, I feel like the current architecture is just so convenient right now. And we don't have any better idea, but my wishful thought, if I may just say something completely ungrounded, is that we need a model that can actually abstract away, summarize, and then learn some knowledge from its past experiences. Almost like from episodic experiences, we need a model that can learn semantic knowledge about the world, the semantic memory. So humans have apparently different memory architecture that says procedural memory is different from declarative memory, which is the memory that's describable through language. And under the declarative memory, there's episodic memory and then semantic memory. And these two things are different, and then they really interrelate in the way they operate and stored. Right now, it seems that we just have one blob of parameters that represent all of the above, which is a problem.
I'd like to follow up on Yejin's point. So this is one good way to think about it, these different kinds of memories. So the kind of knowledge, so the knowledge of how to bicycle or knowledge of how to walk is not of the same type as the one which is in these models. I wanted to build a little bit on what Natalie said, and this is something which is like a serious concern to me. We went from supervised knowledge to supervised training to unsupervised training, and we thought that's a good thing. But going with the unsupervised training was also the aspect of uncurated data. So the data which is being thrown into these things is uncurated, which means that it brings in a whole lot of crap. Basically, misinformation, disinformation, stereotypes. They will all say that doctors are male and nurses are female. They probably believe that Trump is the president of the United States. They probably believe that vaccines will cause chips to be implanted in your bloodstream, right? So all this stuff, because it's all there on the web, it is all there in these quote sources of knowledge. And to me, this is actually very scary. Okay, I'm sure there are other talks which will concentrate on the scary part, but as a purely scientific person, question, I feel that this is why that notion of scientific understanding is important. Whereas when we do a physics experiment, I mean, that is God's own truth, or maybe it's Newton's own truth. Okay, whereas something that some idiot has typed in and we suck it in, and then we regard that as a source of knowledge on COVID vaccines. I mean, okay, I end there.
Well, let me push a little further as to how people should react to that for the sort of technological foundations which you're officially being grouped under. I mean, so in recent years, there's been a lot more talk about socio-technical systems. Something I learned the other week was actually the term socio-technical systems was first coined in a study of English coal miners 80 years ago. So it goes to show there has been interest in socio-technical systems further back than you might think. So maybe we should be talking about socio-technological foundations. I mean, what can we be doing in terms of ideas of interpretability, avoiding reproducing private data and other things? Can we be taking steps that would build any of the properties that we'd like into the technical base of the models that we're building?
This is a huge topic, of course. There are so many pieces to it. I'll just talk about one piece, understanding sort of the provenance of where you're learning, tracking that as you're learning. And it's very hard to do with the amount of data we have. But the provenance aspect is something that I think we recognize as important, but we have not made much progress on. And it is something that matters. As Jitendra says, there's a mixed bag. And of course, at some point, you might arrive at a place where there are genuinely two alternate belief systems that are in conflict with each other, which I think is true for the world that we are in right now. And at that point, there's a question of, how do you actually even reconcile those? But you actually have to include that in how you come up with the output. You have to think about both tracking the provenance and recognizing maybe there's at least two worldviews, and together that arrives at maybe different outputs. And that's something that we need to integrate into how we build these models.
One thing that strikes me about GPT type models is that you can query with a prompt, which means this is what you should think about. It doesn't seem to be as easy to tell it to forget something or not to use something, which you can do with a human. So some kind of an orthogonal subspace of the prompt, if that made sense. Yeah. So that would be interesting, like to edit what it's learned.
So maybe not perfect solution toward that yet, but some of the unsupervised inference time algorithms, including work from our own group, try to address that issue to some degree. Meaning, for example, if it's about to generate toxic language biased against underrepresented groups, then we can try to undo the harm by having toxic expert talking down on the kind of words that toxic language model wants to generate. And we can also do this more in a hard constraint manner as well through, for example, neurologic decoding, in which we could have hard constraints not to talk about certain lexical items, although that would be a crude measure. But going forward, it seems that based off from some of the earlier comments from Kavita and Jitendra and also Natalie about the scariness of what GPT-3 learns from raw data, it strikes me that humans develop so much, we invest so much into learning material for teaching humans. And in fact, depending on the quality of learning material, students can learn drastically differently, whereas we may not be investing as much into high quality training data or high quality knowledge that's guaranteed to be truthful. So it seems that maybe we're over-investing into machine learning algorithms and try to find the magic answer just through algorithms when without the data, without not just the raw data, but also curated knowledge that's guaranteed to be true. We don't seem to be able to just somehow create GPT-4 magic that's ethically all correct and fact-checked.
So, I mean, I think there are interesting ideas there, but like, I think there's still this question of how we actually sort of have models that implement them, right? So like human beings have this sense of information they've heard from different people, and they're sort of able to keep track of that so that they don't just blurt out things that they happen to hear some politician saying on TV without any sense of context. And then we've also got some sense of the world changing so that we know some of the things that we heard years ago might not be true anymore. Whereas like at present, none of these models, whether just the language ones like GPT-3 or the more vision-y ones like DALL-E or Clip or something, they don't have any of that. I mean, can we start to build that into our models?
Yeah, in the future, I hope. But I think the key is knowledge. We cannot not worry about knowledge anymore when the AI models learn so well from raw data without correct knowledge.
Okay, you said yep, but how can we possibly do it?
Actually working on knowledge model as a thing. And study how to integrate that into language understanding or any neural understanding and generation models.
I was going to say that maybe focusing on having the model generate better explanations, because I think the saliency methods are probably not a good match for this kind of model. And I haven't seen a lot of work saying they are. And there's various reasons why like use of multiplication as an attention is actually very problematic for current saliency methods, because the saliency is just, weights to the input, pieces of the input, which is a very poor explanation in general. So maybe focusing on how the model can explain why it's doing something or think something. Some explicit mechanism inside the architecture might help with all of these.
Okay, Jitendra, you had a comment?
Yeah. So I think that we should revisit some of the classical ideas which go back to sort of logic and conversational postulates and so forth, going back to 60s and 70s. I mean, so logic, right? There is some nice properties of logic, right? That logic is normative. And probability theory has the same characteristic that with certain axioms, it says this is what correct inference is about. So in those days, we used to talk about normative theories, and then it carried into the database world where they talk about curation and then being consistent and all of that. And now we've gone and then those are normative theories, and now what we have is our descriptive approaches. So they are basically sucking up whatever is out there and then spitting it back at you, with no notion of of imposing sort of normative standards. So maybe you can say, yes, this is democracy at its best or worst, right? But I somehow don't like it. I actually now am going back to I started as a student of John McCarthy like 40 years ago. And for McCarthy, why logic was so important was because that was the one correct way to reason. And there are versions of probability which have the same characteristic. And we have given that up. Okay, so therefore we can have now you could say that's good because that enables us to store inconsistencies which will happen. But have we given up way too much?
Yeah. Well, that can maybe lead into the last topic. So before we run out of time, we should have a little bit on evaluation. I mean, the importance of evaluation was something Yejin mentioned in her talk. But among the questions that we've got, one closer to what Jitendra was just talking about, is how can we develop tests that better differentiate between memorization from intelligence and the sense of being able to reason? But I think as well as that, I think we want a lot more by evaluation, because we also want to be able to evaluate our models for issues such as bias or for what effects that they have in the world when we look at things like recommendation systems. So what kinds of evaluations should we be building that we don't yet have that will allow us to better interrogate these models? Who's game to try that first? Yejin, Natalie?
Sure. I was just trying to see if others might want to chime in first, but no, I love to talk about this. So I think we need a leaderboard, because everybody who has a model wants to climb leaderboards on ethical judgments like biases and toxicity and all that, so that even people who don't care and who think there's no problem, they're not biased, there's no serious bias against racism or sexism. Because by working on this research area, I learned that actually a lot of people in our field genuinely think that there's no problem. Some of them don't. It's just they don't talk about it too publicly about it. But I think we need really a leaderboard for that sort of problems as well, so that that line of research gets a lot more support, or research activities as well. And something else I want to emphasize is generative evaluation, or evaluation that makes the model to generate an answer, as opposed to choosing which of the 4 choices might be the correct one when one of them is guaranteed to be true. Because the problem with the multiple choice question is that there's always a superior dataset biases that are in the data that sneak in somehow. And we end up measuring how well the model can effectively fine-tune without actually being able to solve the underlying task in a natural way. That in the open world setting, for example, there's no oracle that can provide us with 4 magical choices to choose from. So
okay. Great. And maybe we should get thoughts from others on evaluation.
So I agree with Yejin. Of course, like our field would advance so much if we could have leaderboards for all of the neglected topics that we think should be pushed forward. I think we fall on the same sort of problems that like our boring old metrics already have, is that they don't really cover the performance the way we quality of performance the way we actually would like them to. And so I think it's really difficult to have a metric that can give you a good understanding of like what an empathetic person would say is acceptable with output of a system. So yeah, working on empathetic systems, that of course would be very, very interesting, but I don't see how to not have a human in the loop and not ask Black people if this is offensive, but have a Black person metric instead. for example.
Yeah.
I think having human in the loop is very important, and that's something we should think about. But I'll also talk about the leaderboard thing. One thing I know in the vision community, so I'm all for creating these kinds of evaluation mechanisms. You really need them, and they need to align with our understanding of the time of what are the problems with the existing systems. But I also very, very strongly want us every 3 years to revisit these things, because what happens is you just have papers upon papers producing tables of comparisons with all of these metrics, and often they drift apart from the problem you're actually trying to solve over time. So not only do we need to create sort of these evaluation metrics, but we need to guarantee that every 3 years we revisit all of them. Otherwise, you end up optimizing the wrong thing. And that's, I see that a lot in different subdomains in the vision community, which Jitendra, you can comment on this, and I get tired of seeing the tables of numbers without actually improving the understanding of the problem.
Yeah, after a while, your success at the benchmark is just success at the benchmark.
Exactly.
But this highlights something that two of the speakers, Tengyuma and Tatsuo Hashimoto, referred to, that it's actually a mystery why these models are learning so much anyway, because all you're doing is minimizing the cross entropy or prediction loss. So why do they pick up this other knowledge, and how do we quantify that? So until we have that, we cannot really have a systematic way to design. I mean, we can do trial and error, but until then, we have no way to design.
Any last thought on that topic? Well, I guess everyone said their piece and we're hit 2:30. So I think there's more questions I would have loved to ask, but I'm afraid we've come to the end of this time for this panel. And so we'll call it there, and I'll hand it back to Percy to wrap up the first day.
Thank you.
All right, thanks, Chris, for leading that really lively discussion. And thanks to all our speakers and panelists today. I just want to reflect a little bit on what we covered today. We covered a lot of ground, and it's one thing that struck me is how the issues of risks and social harms showed up in basically every session. This is something absolutely that everyone should be thinking about. And of course, we'll discuss it more intensely in session 4 tomorrow. I do also want to stress that foundation models is fundamentally not specific to language. It's about self-supervised learning on data, and that data can be curated, multimodal, grounded from simulation or interaction. So a lot of these axes are kind of orthogonal. But it will be interesting to see how they will fare in vision and robotics, given the impact and what we've seen in NLP so far. And especially in the last session where grounding, interaction, and physics have been brought up as really fundamental to progress. Also, it's pretty clear that foundation models have problems. I think every single speaker mentioned something either technical or social. And I think a big question is how we react to this. Do we take steps to improve the data or the architecture, essentially staying with the paradigm, or do we need a kind of a bigger reset? So on that note, I'll leave you to think about that question, and I'll see you tomorrow at 9:30 Pacific for session 3 on industry and applications.